So, and the tutorial today, it will be the first part will be from 9 to 10:30 Mountain Time. And then there will be a break from 10:30 to 11. And then the second part will be from 11 to 12. And any changes to the schedule, we'll let you know. Hope you guys are having a good weather as what is in Albuquerque. All right, so the title of our tutorial is Better Scientific Software, and we'll be hearing from David Bernholdt, Patricia Grubel, and David Rogers. Thank you very much, and go ahead, all yours. Thank you.
Thanks very much. Good morning, everybody. So if anybody wants to follow along with the slides, they should be on the Google Drive for the meeting, or you can follow this link that's on the screen and go to today's tutorial, and there's also a link to them there. So I'll skip through this slide. I'll explain more about it later. But first, I want to start by introducing us today. We'll be talking to you for a couple of hours. I'm David Bernholdt from Oak Ridge National Laboratory. Over there is Patricia Grubel from Los Alamos, and David Rogers, also from Oak Ridge. We're members of the Ideas Productivity Project, which is lately funded by the DOE Exascale Computing Project to support, ECP is funding us to support the needs of the ECP project to do a better job with developer productivity and software sustainability. But a lot of what we do in terms of tutorials like this and other things are also outward facing because a lot of this applies to just about anybody. And so we engage in various activities. If you want to find out more about these things, there's a DOI at the bottom of the page. You can follow that link. If you like what you hear today, well, let me go one more slide before I say that. One of the other things that we're trying to do is to build an online community around resources to help people improve their scientific software practices. So this is kind of a recognition that you can Google all you like about software engineering, and you'll find lots and lots and lots of things, because lots of people have opinions about this, but most of it that you can find out in the wild doesn't have much to do with scientific software. And we who work in this space understand that scientific software tends to be a little bit different. And so we're trying to focus on identifying resources and concepts and approaches that are helpful for scientific software and expose those more easily to users. So you can go to bssw.io, betterscientificsoftware.io, to find that information. We also welcome and encourage contributions. So if you have a resource that you found useful that we don't have on our site, please consider contributing. And so if you are interested in the kinds of things you hear about, you can follow us in a couple of ways. We have a mailing list that sends just a couple of messages a month, mostly about our webinar series and other events that we organize. If you're going to conferences, we sometimes try to organize technical sessions or birds of a feather sessions or things like that there. And then the BSSW site has a monthly digest that highlights some of the new content each month, including our new blog articles and events and other things. So those are a couple of ways to keep track of what we're doing. Another thing that we are striving to do a better job with in this tutorial is being more inclusive. Computing is rife with terminology that's considered harmful and exclusionary, and we support efforts to use more inclusive language. We're trying to do it ourselves in this tutorial. So for example, back in the old days, the default branch for Git was often called master, and many projects and the Git code maintainers themselves have replaced this, so the default is now main. We've tried to do some of these things in our tutorial. If you want to know more about this, there's a couple of links on this page that you can follow to learn more. And we also encourage you to let us know if you spot anything in our tutorials that we need to fix. The website is, as I mentioned before, sort of our archival site for all of our tutorials historically. So each tutorial has its own page and has links to the presentations. We have recordings in many cases and things like that. So you can go and find other content that we've done that we don't have time to do today, things like that. And then I want to go back to this slide 2. Slide 2 in all of our presentations has a license for the content, requested citation, and acknowledgements. So this is kind of a first example in today's tutorial of what we think of as a best practice. One is make your license and your preferred citation easily findable. And sponsor acknowledgements rarely hurt. Usually sponsors like to be acknowledged for their support. So we'll usually skip over slide 2 in most cases, but that's what's there. And then we want to interact with you. So during the tutorial, please ask questions. If you're online, please use the digital raise hand. And I don't know if we'll be able to unmute you, but you can at least put questions in the chat. And we have interpreters if we need to, who will be keeping an eye on things. We also have a mailing list that you can send us questions afterwards, or of course you can go back to the tutorial web pages and refer to the content. I think this is being recorded, so we'll probably have links to recording later on if you want to review what we've discussed as opposed to just the presentations. So today we're going to cover a lot of ground. We're actually, they've given us several sessions in today's meeting. So we're going to be covering a variety of topics. I'm going to proceed next with a motivation and overview of best practices. We're going to talk a bit about scientific software design and refactoring. After the break, we'll talk about collaborative software development and packaging. Then after lunch, we'll have a bit on testing strategies and reproducibility. And hopefully a lot of these talks you'll find will refer to each other. So hopefully we'll reinforce things as we go along. And as I said, we welcome questions also as we go along. So please don't hesitate to raise your hand and ask questions. And with that, I think we're ready for the next presentation, and I'll take any quick questions if there are any. All right. So a fundamental message that we want to try to convey today is that science through computing is at best as credible as the software that produces it. So most of us here are engaged in the scientific enterprise in some way. That's why we go to a conference about improving scientific software. And this is really at the heart of why we think better software practices, better software engineering are important. It's a real challenge these days. We have, there's kind of a cycle, especially in high-end modeling and simulation, where we get a better understanding of physics, and that allows us to produce a better model of the physics that we implement in our in software, which requires more diverse and complicated solvers, which require more hardware to run, and then we get more hardware, and that enables us to do simulations, which we compare with experiments maybe, and we further advance our understanding of the physics. And this is, in some sense, a positive feedback loop. It's positive for science, but it also makes our life a lot more complex because the codes are getting more complex. There's a lot more moving parts that need to work together. More and more these days, we find projects that are project teams that are comprised of larger multidisciplinary groups, often also multi-institutional groups working together. So in order to bring all the expertise that's needed to the table, but at the same time, we have to have ways for all these people to work together around the software, which leads to concepts like separation of concerns that we'll get into a little bit more. And fundamentally, to engage all these people productively requires more than just letting everybody have at the code in an unorganized fashion. And then In addition to this, we are in an age now of heterogeneous computing. And so we have an increasing number of different computer architectures that we're trying to get all this software to run on. And we have requirements, scientific requirements, and we have requirements related to the platforms and what's the next platform going to look like and things like that, that may not be known from the start. And so we have to also think about the design and the software engineering processes that will allow us to adapt to those future changes more effectively. There's lots of challenges with this. There's both technical and sociological changes. On the technical side, any part of this huge software system that we're often dealing with can be under research at any given moment. So you might be modifying the physics, you might be messing with the numerics, there might be computer science issues that you're trying to improve upon. And while you're doing this, the requirements for what you're trying to implement change as your understanding of the problem grows. Most of us are working in a space where we're trying to do things that model the real world. We represent that by floating point numbers, which bring additional complexities to the challenges of trying to verify that these things are done properly. And so kind of the end result is that the real world is messy, and this gets reflected in the software that we create to model it in various ways. And then in addition, we have to deal with this increasing architectural diversity that I mentioned. And at the same time, we have sociological challenges that we're trying to deal with. The biggest one is that we have competing priorities and incentives. So our sponsors often care more about the publications than they do about the software. And we have to make decisions as the project leaders and the people doing the work about how to balance development and maintenance with research in a way that we can satisfy the sponsors, as well as keeping the software in a state that we can use it as a tool going forward. And of course, we have limited resources with which to do this. We have to interact with people who oftentimes have different backgrounds, different expertise, and that can be challenging. Sometimes people don't even speak the same language scientifically. And I've been on projects where we've spent, even a year just trying to get the terminology sorted out to make sure we're using the, same term to refer to the same thing. So there's lots of different things we're trying to deal with. And if you don't pay attention to these things, problems can arise. These are a couple of high consequence software related failures that you may have heard about. Back in the 80s, there was a computer controlled radiation therapy system which suffered from poor software design, development, and testing practices that let through flaws that allowed at least 6 cases of substantial radiation overdoses to occur before they caught it. And you can read about this. The Therac 25 is kind of an infamous case in software engineering. And then something like the Mars Climate Orbiter, 1999, it was lost because it was trying to do a burn to insert an orbit around Mars, and that went wrong, and they lost the orbiter. And it turns out that it was because the interface between 2 pieces of software didn't follow the specifications. One, they used 2 different units of measure in the 2 different sides of the interface, and it wasn't tested well enough to expose that. And so they lost this, billion-dollar spacecraft because of it. And really the tragic thing about the Mars Climate Orbiter is that people had recognized this and they were trying to raise concerns about it, but they didn't follow the proper procedure, and those reports got ignored. So sometimes the impacts are a little more subtle, though. This is a story from the Flash Astrophysics team. It's one of our colleagues who works on the tutorial team. Back in 2005, the Flash team had access to special access to BGL, one of the largest machines in the world at that time, for dedicated to run. So they had less than a month to prepare for this 1.5-week access period that they had. So they did some quick and dirty development in the code of a particle tracking capability. And because it was kind of quick and hurried, they introduced an error, and it took them 6 months after the run. They got the run through, but it took them 6 months afterwards to develop and apply the post-processing tools to back out the problems that that error introduced. And so the lesson here is that Flash had a software process in place. It was tested regularly. They worked very hard at the design and the software engineering processes. And because of other factors, this was a case where they couldn't apply the full rigor of their process, and they suffered as a result of it. And in this case, they managed to get the science out, but it was much delayed compared to what they had originally hoped and planned. And this leads us to the concept of technical debt. How many folks have heard of of technical debt? Okay, good. A lot of folks. So this is the implied cost of rework due to choosing an easier or a more limited solution rather than implementing a better approach from the start. And it's like monetary debt. The more technical debt you accumulate, the harder it is to pay off. And it can manifest in a lot of different ways. It increases the cost of maintenance. Parts of the software may become unusable. Parts of the software may become hard or impossible to verify and result in questionable results. May take more time to on-ramp new developers, and ultimately, in various ways, it reduces your overall software productivity and therefore your overall scientific productivity. So this is something that we strive to, it's now talked a lot about in the software engineering community at large, and this is something to be aware of when you're making decisions about your process through your software development and the practices that you choose to apply in your project. Another reason why we think attention to the software engineering is important is because a lot of us are using valuable scientific resources. If you're using a major supercomputer today, these things are typically $100 million, and they cost millions of more per year to operate. And so if you get a significant allocation of computer time, it can be worth literally millions of dollars. You may not have to pay for that, but it's a limited resource. And you're competing with others to get that allocation on, those DOE systems that I've shown on the right side of the slide. The requests typically outstrip the time available by about a factor of 3 and sometimes more. So the sponsors will wonder if you're being a good steward of the resources they're providing, and your concern should be, are you getting the most science out of the allocation that you have, aka the most scientific productivity that you can get? So the basic message that I would like to take from these thoughts is that good scientific process requires good software practice, and good software practices increase scientific productivity. And at the same time, good software practices also increase software sustainability, which in the long term also increases scientific productivity. So it's not exactly a cycle, but basically my argument is that good software results in good science or better science. So what are good software practices? Well, unfortunately, there's no universally agreed set of best practices for scientific software. The specifics are going to depend a lot on what your software is doing, who's using it and how it's used, and the team that's developing it. But there are a variety of recommendations that we can look at to get some ideas of how to approach this question. So, excuse me, one is a paper written by Greg Wilson and some colleagues back in 2014 called Best Practices for Scientific Computing. Excuse me, and I'm going to sort of scan through some of these. I encourage you to take a look at these slides in more detail, or take a look at the paper, actually, for things to think about as kind of a takeaway message. But writing programs for computers, for people, not computers, and at the same time letting the computer do the work, any work that's repetitive, work in terms of small incremental changes, don't repeat yourself, and plan for mistakes, which is essentially about testing in large part. Here's a classic lesson: optimize software only after it works correctly. This is optimization is the root of all correctness, is the enemy of all correctness. So, you want to make sure that the code is actually doing exactly what it's supposed to do before you optimize it, which can screw up what the compiler makes it do, or the system that you're running on, depending on the hardware. Also, in the documentation, so of course we're all doing, documentation that follows along with the development of the software in a timely manner and things like that. But also, it's important to think about what it is you're documenting. And as somebody said, you can read the code to understand that the code says set A equal to B, right? What you want to know is, what are A and what are B, and why are you setting them equal, or why are you incrementing that, or whatever. So document the interfaces, document the reasons, not the specifics of the implementation. If you have to do a lot of explaining of the code in terms of documentation, think about refactoring it to make it simpler instead. And it's useful in many cases to embed the documentation for a piece of software in that software, because that's where people will be looking to try to understand things in the first case. But it's better to have some documentation sort of no matter where it is. And also, I don't think anybody needs to be urged to collaborate these days, but there are certain kinds of collaboration that can be really useful. So we heard yesterday a little bit about the use of code reviews. So having other people review code that you've written will help you improve your code, will help them understand the code, and will give more people confidence in the code before it goes into the code base. And that's an adjunct to the testing and the CI and things like that we are encouraged to apply. Sort of the extreme version of code reviews is pair programming, where you're actually working on these things together. And then even things like an issue tracking tool is a means of collaboration, because it's a means of documenting for everybody involved with the code, which may be your development team and your users and perhaps others, what's going on with code, if you found an issue, if you need a feature, if you want to track the progress of a development or things like that. All right, so these are some ideas, but as a couple of years passed and people commented on Greg's paper, he decided that maybe the best practices was too high a bar to set for most people. So they wrote, mostly the same people, wrote another paper called Good Enough Practices. And you can see there's more detail here, but not necessarily, the concepts are not necessarily that different, but there's some discussion about how to manage data management, which is new. There's some talk about how to work on manuscripts together in more effective ways. Things like, I like 2E, test libraries before relying on them. That's something that a lot of us forget about. We are encouraged to rely on other people's libraries rather than implementing our own versions of these things. But then how do we know that the library is doing what we expect it to do? And when that library gets updated, how do we know that the library is still doing what we expected it to do and something hasn't changed under the covers? And then now, maybe the documentation is lying. So we should not, trust but verify is the strategy for that. Let's see. So more talk about collaboration. So here's where we have a recommendation to make your license explicit, make the project citable, create a shared to-do list for a project, which is something that many projects do within the issue tracker. So you can have, you can use the issue tracker not only for bugs, but also for things you plan to do, and then to prioritize those and things like that. They're now talking about suggesting ways to organize the project to make it more effective. Keeping track of changes is a lot about version control and various aspects of that. So these are a whole bunch of practices that are really helpful. And I think, once again, this is a list that people have found, useful. It's not definitive. Your project may decide that, some of these things are not for you and that other things that aren't listed here might be more important. And that's a really important part of figuring out how your project team wants to work together on the software. And I'll just mention one other source of best practices that might be interesting. This is not about scientific software. This is the Linux Foundation, who support a lot of the basic infrastructure software that is used in the Linux environments, that all over the place. This is, things like OpenSSL and, various low-level libraries and things like that. And they have a structure that they've set up which has 3 different grade levels. And there are very few projects right now that are getting silver or gold. Most are just focusing on getting passing grades. They end up with a series of must and should criteria, and I'm not going to go into all the details, but this is a great resource in part because they have justifications for every single one of these recommendations. So you can go to the site, which was on the previous page. The link is there. And by the way, the website that I pointed to before has all the links pulled out onto the tutorial web page. If you want quicker access, you don't actually have to go into all the slides to get them. But you can see the justifications for all these things. And so there are some important things here that we haven't seen before. So this is, of course, an open source community. So they want to require open source licensing, some rules for project oversight and how the project works. In addition to using version control, they want uniquely identified version numberings and rules for doing that. How are you going to identify your versions? They want release notes. They want not only a bug reporting process, but a vulnerability reporting process. This is obviously very important for infrastructure software, but it's also, so these are like security vulnerabilities and things like that, but it's also increasingly important in scientific software. As we heard yesterday, we heard talks about systems that effectively expose resources for the public to access in some way. So these are things that we increasingly have to worry about in order to expose our science and our tools to the community. Let's see, so in terms of quality, there's talk about testing. They encourage coding standards, which is also new from what we've heard before. They want a clearly defined installation system. Build and installation are both in there. They should be together, but they don't list them that way. They want somebody knowledgeable about security practices to be part of the project. They encourage the use of both static and dynamic code analysis tools. These are a lot of things. We had a conversation just yesterday with somebody who tried a linter on a piece of code and came up with thousands and thousands of errors and was immediately turned off because it was just too much to handle, right? But it was, these are the kinds of things that if you can sort of get in there and work through it, and then you can, once you get a handle on that, if you can keep the errors out, then things will be much cleaner. So you have something to aspire to. And really part of the message of talking about this last one is that, as I said before, software engineering advice often needs adaptation for scientific software. So don't necessarily think that because you see it out there as somebody saying this is good software engineering practice, don't think that you have to adopt it in your scientific software project just because it says so. There are many things that we can adopt and probably should adopt, but some things need some adaptation, and you need to be thoughtful about that, and you need to be willing to work through that. So it may take some trial and error. You may try things, try out techniques, try out adaptations of techniques, and you might find that they don't work so well for you, and you may have to go back and try again. So don't be afraid to experiment with these things. And it can be a little bit frustrating sometimes, but the net desire is to improve your practices. And so this leads to the next question of how much time and effort should we spend on software engineering? And if you're involved in the scientific enterprise, the answer probably isn't that you should spend all your time on making the absolutely best software from an engineering perspective that you can, because you're not going to get rewarded for that, unfortunately. So you should include just enough software engineering that you can meet your short-term and your longer-term scientific goals effectively. So there's two parts to this. It's keyed to the science that you want to do. And also, I like to focus on that longer term. It's often fairly easy to figure out the short-term side of things and to figure out where the engineering is going to benefit the short term, right? It's the longer term and your ability to use the software as a tool going forward and keeping it honed that is maybe more challenging to see, but is also the bigger value in the long run in this kind of investment. So we've developed a process that's really quite simple. So I find I grew up as a chemist, and I got into software engineering because everybody I looked at was having such problems. And I thought, well, there must be better ways to do this. And so I started reading up about it. And so we want to improve our software processes. There's a term for this, software process improvement. And like most software engineering things, it really turns out to be pretty simple, or at least this does. We call this PSIP, Productivity and Sustainability Improvement Planning. And what we're trying to do is to instill new processes in your software development that will improve your productivity and lower your costs. So if you look at the graph on the upper right, we have some old process that has a certain cost as you go along to make your technical progress. And we want a new process that will bend that curve over. And we recognize that there might be a cost in the beginning to putting it in place and getting it all working and all the rough edges sorted out. But in the long run, the goal is to bend over this curve. And so here's the process that we recommend. First of all, sit down with your team and identify the pain points in your scientific development processes. And there's a tool that we've developed. There are other ways to look at this, a tool called Rate Your Project, which helps you assess your project in different axes and helps you identify different ways that you might want to think about improving your software processes. And then you pick something that you want to improve. So just target one thing at a time. You should target processes and behaviors, not just tasks. So you say, well, we need to improve our documentation. So the process improvement is not going and updating all of your documentation. The process improvement is, how do you ensure that when the code gets updated, that the documentation also gets updated to go with it, right? So then that's something you can carry forward. It's not just a one-time task. And then you agree on a plan to work through this problem. You identify markers of progress so you can track your progress along the way. What are sort of key milestones that you can say, this is getting better? And then finally, how do you decide when you're done? And it doesn't have to be perfection. It just has to be good enough that this is better than it was before. You should write these things down. We have a simple thing called a progress tracking card that we have some examples of people who have been through these kind of things before, how they've sort of sorted out their path through these improvements. And then you work your plan, you track your progress on the progress tracking card. And when you're done, you have a little party, and then you're ready to pick a new pain point and move on to another round of improvements. So you have a small process of small continual improvements, and you keep bending the curve and improving things. And one of the things that this BSSW site that we developed, is meant to do is help people provide resources to support these kinds of things. And so you can see that Rate Your Project is a separate site, but you can see the progress tracking cards. Well, actually, so I should point to the PSIP URL is hanging off of bssw.io. And there are other articles on bssw.io. There's some resources elsewhere and things like that. So this is, hopefully this is one way to get you started on these things. In today's tutorial, we have a limited amount of time. And there's obviously a lot of topics that we could talk about to improve scientific software. We're going to try to focus on a few where we feel that the software engineering advice out in the wild doesn't necessarily address scientific software. So we're going to try to focus more on those topics. And these are the topics we're going to have time to hit today. If you look back at some of our other tutorials, especially in some of the longer cases, we have some other content that may interest you as well. So you can look at some of the past agendas and see things there, or talk to us if you are interested in other concerns. And so with that, that's kind of the, hopefully you're on board that this is a useful thing to think about. Happy to take some more questions at this point if anybody has any. And then we can move on to the next presentation. Yes.
If you can use a microphone so that the folks from afar can hear you.
So do you think that the languages like Python, where the type is automatically deduced, so are they not good for good scientific software practices?
So these kind of auto typing languages are, they have potential dangers. You have to be more careful when you're developing using them. But with discipline, they can be used effectively and they can be very productive. So there are trade-offs there. There are trade-offs in almost any decision we make about how to program things. And so auto typing languages like Python and things like that lean towards the productivity side of the equation. But with due care, yes, you can use those effectively.
Hi, so I don't want to get too far ahead. Maybe you address this in the next section, but I noticed on that last slide you showed there was a list of topics that typically there aren't good resources specific to scientific software.
Yep.
And I noticed not on that list is the fact that you have to deal with non-software engineers touching the code. And I think that's probably problem number one that we run into on a regular basis, especially for people like you and me who are started off as scientists and sort of were maybe not dragged kicking and screaming into the software world, but kind of fell down that slope over time.
Right.
So I'm curious if that's something you're gonna be addressing.
So I will say that's one of the many sociological issues about working on scientific software. We're not really going to address that except around the margins, I will say. But it is, I don't want to diminish it, right? You've pointed out something that's very important. I live in a world, one of the things that attracted me to the DOE labs is the group science, right? And so I've been involved in this since I was a postdoc. And I find that, and so I've been working in these groups for a long time, and I guess I have developed strategies that I've probably internalized to work with these folks. But I've seen it in other contexts where groups get together for the first time, and there's all kinds of challenges with communicating and things like that. And so that's something that we can talk more about, maybe at break or things like that. There's lots of experiences, but we'll only touch on it around the periphery here. There is one up front. Get your steps in.
Yeah, thanks. Great start to it. This is kind of along similar lines about just you're having non-software engineers. And part of that, one of the things that I've struggled with communicating to some of the more just science-focused people that are touching the software is the difference between writing well understandable, well-documented code and just writing essays of comments internal to source code. And I've still struggled how to communicate that to people, where it's like you don't want them to disengage from the documentation progress, a process, but you also are essentially telling them, you have to tell them indirectly that their software is too complex if they need to write it, if that
Yeah.
much comments. And I was just curious if that, trying to balance that, if you have any comments on that, because that's, sometimes you get a piece of software like, oh, it's well documented. And then you're like, well, there's actually only 8 lines of source code here and 30 lines of comments.
Right.
And so, yeah, I was just curious if you have any comments on that.
Yeah, again, these sociological issues, they're hard to at least develop training materials for. I would say one of the things is perhaps to make that an emphasis of code review processes and try to train people about the differences between, good in-code documentation and when it might be an indicator that there is maybe a better way to do things if you need that much explanation.
Okay.
And or maybe a better way to document things. And try to maybe have the software engineering folks reviewing the code that the scientists are writing and trying to just sort of slowly convey this piece by piece. And not just going in and saying, you always do this, and making an attack on the person, but then trying to get at how to get them to see a better, more useful way to document by, sort of interacting with the code they've written as opposed to the comment and the difference with the comments and what you would like to see.
Okay. Yeah. And I guess the review process would really help. Because often that happens after like 3 months, they just give you a piece of software.
Yeah. Well, and another thing is don't let them go off that long without.
Yeah. Thanks.
Yeah, thanks.
Okay. Hi, David. It's Maggie here again.
Yep.
So 2 things. If we can please remind in-person people to go to the mic at the front. If you have questions, thank you. And then we do have a question suggestion here on the Zoom chat. This is from Janine. I'm going to read it. A suggestion for your training concerning inclusive language. Scientific software is not equivalent to modeling HPC. Scientific software also includes observational software. While the concepts in your talk are broadly applicable, a simple change of language in your presentation will help software developers working in the observation space feel more included. Can I comment to that?
Yeah, that's a very good point, and thank you. I will admit that the developers of this tutorial material, mostly come from an HPC simulation-based background, and that's a lot of what we do in DOE. Although there's certainly plenty of experimental and observational stuff going on as well. It's just the space that we've been working in. So yes, we are biased in that way, and that it's a very valid criticism of the way we've cast things here. So yeah, it's something that we need to take on board.
Okay, thank you very much.
And thanks for me.
Yeah, any more questions? Or otherwise, I think we're ready to proceed.
One more here.
Okay, thank you.
So you mentioned some of the competing interests in terms of incentives for performing good software engineering. And yeah, I mean, as a young grad student, I feel really strongly about being good about my software engineering practices, and I definitely feel the benefits for myself whenever I do it. But yeah, I certainly feel that external pressure to publish. And so I'm curious to know if any of the folks in this project have spoken about an ideal world where there's a different incentive structure. What would that look like potentially to really motivate good software engineering practices?
Yeah. So this Ideas Productivity Project goes back to about 2014, and that was the first case where DOE actively supported a project that was not, they don't support software engineering research, and it was really a project that was focused on improving software practices and improving software. And associated with that from the beginning has been trying to raise the visibility of software and the developers of software and the culture around software and try to instill cultural change. And there are now a lot more, so we've been doing this 10 years or so, and there are a lot of other organizations in this space. There are many who were there before us, and there more have joined. And there's a growing conversation that's trying to really change the culture. It's a very slow process, especially with research sponsors, who are kind of the biggest drivers in some respects. So this is, it's a big, important thing for people to think about. It's also a very long-term thing, for better or worse. I would encourage you to become active in this space and find opportunities to join communities that are relevant to your interests and where you think some of the bigger problems lie, and work with them to have the conversations that they're having with, you know, the sponsors and the others who, managers and others who need to help us make these changes in the long term.
Great, thank you.
I think I'd just make a short comment on that, that there is kind of a research software engineering initiative. I feel like that's started. A little, I think there's even a conference that is happening. And I think I've been reclassified at NREL as a research software engineer. So that type of stuff has been happening. So that helps kind of make a track. So you're not just like focused on publishing. There is an initiative, because software is so important to us, that there is that stuff going on.
Yeah, there's a lot of organizations. There's this sort of emerging idea of research software engineers and research software engineering as a career track, a recognition of what a lot of people are doing already, and trying to make that better recognized. There's an organization called us-rse.org, the US Research Software Engineer Society Association, which is just an affinity group or a community of practice that's getting more and more organized. They're having a conference, their first in-person conference this October. So you go to usrse.org, they have some webinars and things like that. So that's definitely one place to get engaged, but there are a lot. So look around at what's going on in communities that are relevant to you, and, you know, find something. USRSE is a great one, but it's just one. All right, we probably need to move on. I don't even know where I am time-wise, but we'll talk a little bit about design of scientific software. And once again, I'll apologize to some of you folks who are more oriented on experimental and observational science. The examples here are going to run towards modeling and simulation type things, but hopefully you can get the fundamental takeaway messages in the same way. And so once again, we talk about this virtuous cycle that brings us to attempts to bring us to a better understanding of science, but gives us more complex software and more challenging situations to deal with. And we've been, over time, we've spent a lot of time working on this distributed memory model of computing, where we just added more and more cores, and sort of everybody was mostly happy. The platforms weren't getting that much more complex. It required more complex software to deal with this stuff. But then we went through this phase change, and now we're talking about heterogeneous computing, and both the platforms and the software are becoming more complex to deal with those things. So we end up in situations where a lot of different pieces of the software may be actively changing, and the subjects of research at any given moment, the software is continuously changing, and we're, you know, pretty much anything we're trying to do with it is different and unique than the last time we tried to do something, because we're always trying to, you know, move forward and explore different situations, do new things with the software. So here are a few design principles that you might want to think about. First of all, as we've discussed, we work in increasingly multidisciplinary teams. So it's not feasible for one person to know everything about the software system or the domain, or, you know, the different types of knowledge that are required. Excuse me. An approach to deal with that is separation of concerns. So basically, this in the larger context, this amounts to encapsulating the different aspects of the software system in ways that people So some people will know and understand the details inside that white box, and others will be able to essentially treat it as a black box. They just call with the APIs, which are of course well documented and well tested, and they don't need to know all the internal details as long as it does what it says it's going to do. We end up working with different types of code components within our code. There are things that are more infrastructure oriented, and then there's more sciencey aspects. They tend to have different considerations. They tend to evolve at different paces and for different reasons. And so it's useful to recognize those distinctions in the way you design and deal with the software, what is longer lasting and what needs to be, able to be changed quickly, what's where the complexity lies and how you're dealing with it and things like that. And then we also have to recognize that codes grow. You have new ideas and you want to implement new features. The code is reused by other people to do things that you hadn't conceived of originally. It has to work on new platforms that it wasn't working on before. So you need to design for extensibility. Even if you don't know what's coming, you want to design so that you have the flexibility to adapt easily to what you think might be in store. So make it easy to add new capabilities or to customize them and things like that. And so here's kind of a picture. On the left, we see sort of 4 different parts of the code. There's parts of the code that are subjects of the research, and there's client code, which is sort of using the aspects of the system that tend to be mathematically complex and more experimental in nature. And then down at the bottom, you see things that are more stable and more of the infrastructure and things like that. And so you want to try to structure your design so that there are these different things and they're separated from each other. So you decompose them into logically separable functional units, and you put well-defined interfaces around them. You differentiate between the public and the private aspects of the code. How many people understand what I mean by that statement? This is something that's kind of common in object-oriented programming, but may not be so familiar in other cases. If you have a piece of code, a collection of code, sometimes there'll be methods that are just for internal use, and there'll be other methods that are, sort of the outside interface, the library, what you expose to the outside users as a library or something like that. And you want to make sure that the things that are meant to be private stay private, that people, even if they exist and people can find out about them, you want to discourage them from using them. In some languages, you can effectively prevent them from using them. In other cases, it's harder. But the private internal stuff is easier to change because you haven't told anybody else about it, right? And if somebody outside is relying on what is, a private method call or something like that, what should be private, then when that breaks due to some change, that's not your problem, it's their problem, right? And so, some ways of thinking about the design that will help you structure things so that you can make these kind of differentiations, and you can make these at multiple levels, right? So you can, just individual units or classes or however you're structuring your code, and you can make them, sort of at component levels or assemblies that work together, and you can do this at multiple scales. And so basically a workflow is something like this. You have sort of the infrastructure on one side, and you have the scientific capabilities that you need on the other side. So you have on the capability side, you have a model of the physics or whatever that you want to implement. And this generates requirements on the infrastructure side, what you need to support that. And you start defining an API, an interface, so that you can separate the model and how that's implemented from the infrastructure. And then you You work on, once you have the requirements for the infrastructure and the API design, then you can work on implementing that, and you can implement the model. And then you, on the infrastructure side especially, testing is really important because that stuff has to just work and be completely reliable for people who don't know anything about it. The infrastructure becomes the black box for the domain scientists typically. And on the other side, the domain scientists need to validate the model, and you need to obviously integrate these things, otherwise it won't work. But you have this sort of cycle where these things feed back to each other. You may find that you want to do something new in the model, and that may lead to some new requirements. You may need to augment the infrastructure to support those new requirements. And so you go through these cycles, but this is kind of a picture of what it could look like, basically. And this is just to help get you into a more systematic way of thinking about design. So a lot of folks that I know go into some project and say, oh, it needs to do this, and they start coding up, and they have some big collection of code that may do what they want, but it hasn't probably been designed in a thoughtful way so that you can actually evolve it effectively with a technique like this. And if you start with a concept like this, then you have the possibility to think more about it more systematically as you go along. And so let's just take a very simple example. This is, you have a wall with a water pipe in it. Outside it's -40, and inside it's nice comfy 70 degrees. And you want to know if your water pipe is going to freeze or not. So we're going to have just a simple one-dimensional heat equation. And we want to identify here how we would divide this up, right? So we have a specification, we want to solve the heat equation with some initial boundary conditions, and we want to be able to apply different integration methods to see how they work. So the infrastructure is the discretization over that wall, the ability to verify IO. We have to say, what the temperature is going to look like over time in the water pipe. We have to apply the initial conditions, things like that. And then the model has what are the actual initial conditions, boundary conditions, and the integrator, the way we want to integrate the heat equation, right? The algorithm that we're going to use. And so we can define some APIs for the infrastructure side of things. We need to process some arguments when we get this call. We need to do some initialization. We need to set the initial conditions and things like that. And I don't want you to dwell on the actual signatures here or even the names of the calls, just to, here's some infrastructure. It's a very simple problem. The infrastructure here is small. Then we have some APIs for the model. So we have some different integrators. We're going to have the option to do Crank-Nicholson or Upwind or FTCS. And we also happen to have an exact solution for this problem. And we also need to compute the L2 norm to figure out what, how we're doing here. And so this is kind of the model side of things. And we can actually implement those things. To extend it to a larger concept, if you're doing in modeling and simulation, especially, we do a lot of physics over maybe 1, 2, or 3-dimensional domains. And on big computers, we tend to divide those domains up spatially and put different pieces of them on different nodes to parallelize the work. And so we end up with an architecture that says, okay, we have a spatial decomposition. And so we have a way to divide this, this space up that we want to look at. And then within each node, we have some, individual workspace where we can apply all the physics we need. And from the decomposition side, we have ways of, sort of exchanging boundary conditions or whatever else it is that we need to know about the rest of the world in which each little square works. And so we have ways of architecting the code. This leads us to ways of architecting the code. So we have these things that worry about the distribution and worry about the communication of information between the different elements of the distribution. And then we can implement a lot of the physics so that it's just looking at what's happening on that node with the boundary conditions that have already been applied to it. And so this allows a separation of concern. So on this decomposition side, we're concerned about the parallelization, the ability to expose, how much parallelism is in this thing, this decomposition, and to scale that out and to optimize those aspects. And within each individual thing where we're applying the physics, We are worried about memory access locally and making that computation on the node as fast as we can, whether we're using CPUs or GPUs or AI accelerators or whatever. And so we end up with things that can help give us a separation of concerns and allow different people to focus on different parts of the code. So we might want the physics to be implemented by domain experts and applied math folks. We might want the software engineers and performance engineers to be looking at some of these other aspects, right? So we can divide things out and people can work more according to their backgrounds. You can do this in the real world. That's not just an arbitrary example. This is an example from the astrophysics code Flash. Now it's called Flash X. They have an approach where they've developed, this is a predominantly Fortran code. So it's not, it's sort of implementing object orientation and componentization and things like that through other, what we might call other methods, but they have the ability to put together components. It's sort of evolved into a framework for complex simulations. They have a lot of different components to do a lot of different types of physics and different environments. It's been used in many situations beyond astrophysics as well. And so they have a structure to do this. And so like everybody else, they went through all this and, you know, at the end of the sort of distributed memory, many core kind of era, they had this model that I've been talking about, differentiate between the slow and the fast changing components of your code. What's the infrastructure? What's the numerics? Understand those requirements well, separate the concerns so that you can implement them, but have different people working on them and things like that. You should design with portability, extensibility, reproducibility, and maintainability in mind. We haven't talked so much about that yet, but we'll get to some of those aspects. And one thing I haven't talked about, but don't design with a specific programming model in mind. This is a key point that we've learned for long-lived codes being able to continue on different hardware architectures. You're better off getting the models and you know, sort of conceptually right at a high level, and then we'll talk about ways that you can actually apply different programming models to that in a few minutes. And so now we get into this area of heterogeneous computing, and the question is, does this cause us to change these design principles we've been following? The answer is no, not really, but things get a little more involved. So most of the changes that we're going to find are in two places. One is the APIs. We may have to modify the APIs to be more flexible in the way the physics interacts with the infrastructure. And we also oftentimes have to be more careful when we start integrating things together because the code becomes more complex. We have to be more careful about when we start bringing it together. There's more opportunities for errors. And so the guidance that we've seen based on experience in the exascale computing project and in the community at large for performance portability is, first of all, to design for hierarchical parallelism. So expect that you're going to have parallelism at multiple levels, design towards thousands of threads, not tens of threads. Expect a hierarchical memory space. If you don't end up on a system with a hierarchical memory space, life gets a little bit easier. But if you try to go the other direction, life can be very hard. You want to pay attention to memory in a way that maybe people aren't used to all the time. So you want to include ways of managing your memory, figuring out what you're using, have clear allocation for your memory and the ability to reuse. So people use pools of memory and things like that. And this helps manage, especially in a hierarchical sense, of where the memory lives and what you're doing with it and things like that. And really from the design standpoint, you should avoid exposing or using vendor-specific options because those will tend to be not portable. So one big example in as we've gotten into the area of GPU accelerators is that NVIDIA was sort of the first to market with GPU accelerators for general computing, and they have this CUDA programming environment, which is C++ like, but it's not C++. And so a lot of people wanted to get running on GPUs, and they put they wrote code in CUDA. And now we have accelerators from AMD, and we have accelerators from Intel, and we have others. And now these people with CUDA code have to find another way to use these other accelerators, because CUDA is a proprietary NVIDIA specific language. And so this is a bit of a challenge, but we're learning now that we're in this multi-vendor environment a little bit better how to deal with those things. I would say it hasn't settled out yet for those who are using GPU accelerators, but I have hope that over time we will get better at the portability aspects for that, for example. And that's also something else to realize about the environment that we live in. Things are changing. And if we have long-lived software, it's probably going to outlive changes in hardware platforms and things like that. So you want to, as we said, you want to think about that, even if you don't know the specifics, you want to think about the flexibility to follow different approaches and try not to embed them in the design, make the specifics for the programming model something that goes over the top. And one way to think about that, so this is another view of that multi-physics PDE style problem. So we have spatial decomposition, and then we have the physics down at the sort of the node level. And then things can get more complex in these new environments where you may need to think about distributing the load, and you may need to think about runtime management and load balancing and things like that. And you may, at the sort of the node level, the physics, you may need to think about having different code that does the physics on different types of processors, because to get the most efficiency. So you might have, you may be able to encode that in one language that works everywhere if you're lucky, but in many cases you'll have to maintain variance, or you'll have to be able to transform the code in some way so that you can take advantage of the hardware, but you want to isolate that and make those blocks as small as possible. And so you develop these abstraction layers that allow you to do that isolation. And then, so to do this, you need to know something about the structure of the code. You need to know what algorithms are going to work for you on different devices, better or worse. That often requires experimentation because the results can sometimes be surprising. You need to know how the data is moving between the devices and between the different parts of the memory hierarchy and things like that. And then you have the ability to start mapping the computations that you need to do to the appropriate devices and memory locations and things like that. And then you have to build into the abstraction layers the ways to specify those different mappings. And so ultimately, the performance from one hardware architecture to another depends on how well you're able to do that mapping. And so some of the underlying ideas behind this is to make the same code work on different devices. Sometimes the compiler can help you with this. Sometimes you just need to have different ways, different specializations to get, to get the right code, essentially the right. Oftentimes it's the data structures and the order in which you're accessing the data and things like that will drive the performance. So one example, especially in the C++ world, is things like template metaprogramming. You can do similar things by hook or by crook in other languages, even if they don't have the sophistication of C++. And then you want to think about within the node how you're getting the work done. So using parallel 4, or if you're using OpenMP, think about how to specify the appropriate parallelism, where the memory that's associated with those computation lives, make sure it's in the right place. There are an increasing number of systems these days for asynchronous task-based computing, which can be more complex. We're not really going to talk about that, but that ups the bar a little bit, but can give you more concurrency. So basically, you need to sort of look at what you need in your code to be able to support these things and try to design for the common elements. And these are, to figure out the right abstractions. And then even if you're using some third-party tool, maybe Cocos for C++ or something like that, you still need to understand the code structure and how these abstractions are, what they're meant to do and how they're working to get good performance. It is still important to see through those things. And so this all amounts to an investment in the design and the thought process about what's under the covers, not just driving straight to the implementation for a single platform. So some final takeaways. We think that the key to both performance portability and longevity of a piece of software is careful design. Extensibility should be built into the design. Stay away from encoding any specific programming model into the design, and think about things like composability and flexibility to help not only with extensibility, but also with performance portability. And there's a bunch of resources here that might help you delve into this more deeply for those who are interested. All right, I'm probably pretty far over time, so I'm gonna, if there are a couple of quick questions, we'll take those, but I want to move on to the next presentation quickly. Any questions?
Yeah. This is Maggie again. We do have 2 questions on Slido. So I'm going to read those if you're okay. It's 2 of them. So one from Michael was wondering if you had any insight into handling balancing performance and good design and their competing trade-offs. For example, well-designed code may be easier to modify, but perform worse than the performant version. But the performant version has sustainability maintenance issues for a design view.
Yeah, so this is a common trade-off that almost anybody has to make. So I think the question is, what are your real goals? Is this, is the software a tool that you want to use for the long term? And can your science afford, or is it something that's more of a throwaway and you really need peak speed at the instant? And then the question of how much your science is going to suffer if you don't get the absolute peak speed. And in many cases, you know, we talk about this, and I often hear people say, well, you know, I'm willing to give up 10% performance for, you know, certain kinds of convenience and things like that. What is that threshold for you? Everybody has it. It may be squishy. It's almost certainly squishy, but that's the kind of thing to think about to help make those kinds of decisions. And so, you know, what performance are you giving up by taking a more sustainable, more general, more portable approach? And those are things that you can do experiments and figure out and have a kind of a measure for that. And is there a second question?
Yes, there is. And this is from Andrew. It's a comment. Recognition of the software engineering and technical advances within modeling is a key focus of concern for the Memusage Model Consortium. For people who are research science but are doing a lot of the core development, their own performance metrics are not publication based.
Well, I'm glad to hear that. And that's something that a lot of organizations are increasingly recognizing. How do you recognize and value software contributions? It's a conversation we're going through at Oak Ridge. We have had RSE groups for about 5 years now or something like that, for example. And I'm glad to see other organizations, we're far from alone in that, by the way, but I'm glad to see other organizations are having those kind of conversations as well.
Okay, thank you. Please go ahead. I believe we do have a break at 10:30.
Yeah.
Okay.
So I'm going to go through this quickly. So we're going to talk about refactoring of software. So refactoring of software is a technique for restructuring of software that keeps the same behavior. So this is a really important part. It's not development, okay? It's changing the software to improve its understandability, its maintainability. There's a variety of reasons you might want to do this. And the point is that it doesn't change the external behaviors. So this is different from just development because you have working code, you know how it works, you understand it, and you have some kind of baseline that you can use for comparison. And if you don't, you need to develop that understanding, and you need to develop that baseline, and you need to develop the tests so that you can be confident that you're getting the same behavior before and after. So motivations for doing this: you want to improve modularity. You want to make it easier for outsiders to understand and use the code, porting to new platforms. And so this last one requires a bit of thought. It's not literally about expanding capabilities, because that's development work, but making the code easier to expand the capabilities of can be a refactoring process, right? You're restructuring existing capabilities or structure of the code so that you can add more capabilities more easily down the road. So this is a typical workflow. You do some refactoring, you test it. If it passes the tests, you can go on. If it doesn't, you need to fix it until it passes the tests. And once it passes those tests, you have to decide if you think you're done with the refactoring. So you're looking at some fairly small chunk of code, and you put it into a larger context and do some integration testing, and you see whether or not it passes that as well, because your unit tests are unlikely to catch all of the concerns and all the behaviors that you might be expecting out of your unit that you're working on. And so you go back and fix things, you keep looping through until eventually you pass the integration tests as well, and then you have a successful refactoring. So if we look at our little running example, I can point you to it later, but we have a couple of different versions of this code that you could look at. One is a monolithic, ugly looking code, and the other is more modularized and reusable and things like that. And so getting from the first version to the second version would be a refactoring process if we're trying not to change the capabilities. And so if you want to undertake a refactoring, you want to know why it's necessary and roughly what you want out of the refactoring. So what are you trying to accomplish, and what the code should look like in some sense. In this simple heat equation example, we have this monolithic ugly code, and you have to change it every time you want to change different integrators and things like that. And there's no reuse, and devising tests is hard, and things like that. And so we want to modularize it and make it more easy to maintain and more extensible. And so what we're going to do in this case is we're going to separate out the utilities. We're going to generalize the interfaces. Yes? We're going to generalize the interfaces, and we're not going to actually change the functionality here, just make it better. So before you start, it's useful to estimate the cost to make sure this refactoring makes sense. You want to check for the coverage to make sure you have tests that are going to, that will give you confidence that you've done the refactoring correctly. You want to create new tests where there are gaps in your coverage. We'll talk about code coverage in a minute to explain that a little more. And we want to make sure you have tests at different granularities. So you want to be able to test at the unit level, but then you want to look at the bigger integration tests because, as we've said, there are almost invariably behaviors that you expect to happen that you're not catching all at the unit level, right? And so oftentimes, even when you're changing code without changing the functionality, you may get changes in the numerics, especially for floating point. So understand what's acceptable, what are your bounds for acceptable changes? Do you require bitwise reproducibility, or what is the threshold? And then you start figuring out how to get from where you are to where you need to be. And you need to make sure in your cost estimates, you need to make sure that you're incorporating the time to develop the tests and apply the tests and things like that into the cost estimate. And so I'm not going to go through this in detail, this little heat equation example, but I'm just going to point out a couple of things. One is the test coverage. So this chart on the right, the code is looking at the code coverage. So we have some tests for this, and we're running a code coverage tool, and the column on the very left says how many times that line of code was exercised in the run that was done, and the hash marks indicate code that wasn't exercised. So before you start undertaking a refactoring, you need to make sure your tests cover the parts of code that you intend to change, right? So some of these things not having test for them may be okay. Other times it may be a gap that you need to deal with. And so then we get baselines. So we run the code as it currently stands to get the numerical results, to make sure that we have a golden answer to compare with. Then we do the refactoring. And in this case, one of the things we do is we don't want to have 3 separate calls for the integrators because they're not identical, but they're very similar. So we try to unify the interfaces and we come up with a more unified interface. And that requires us to do some other things, which are shown here. We have to, one of the integrators requires an initialization step that the others don't. So we can deal with that by saying, well, if we're using this integrator, when we call the initialization step, that actually activates. Otherwise, it's just a no-op. Basically, you make the call, but it doesn't do anything for the other integrators, right? So simple things like that that will allow you and having a unified interface for the different integrators so that you can have one call, and under the covers it figures out which integrator is supposed to be calling and does the right thing. And then you compare this code, you run it, you run your tests again, you make sure that it passes the test, you compare against your baselines, and you decide if you're done. And so in a real world example, the Flash team needed to change their adaptive mesh refinement library. So they had been using Paramesh, which was no longer maintained, and they wanted to replace it with a library called Amrex. And so this is a sketch of the process that they went through. We'll go through this in a little more detail, but quickly. But there are a couple of key points beforehand. So they did the cost estimation exercise. You have to include, this is an actively used code. So they needed to include not only the development time, but also consider the disruption to the production science that might incur while they were making these changes, right? So somebody could work with an old version of the code, but it impacts the development of new capabilities because it can be hard to make major refactorings at the same time you're doing new science development. You have to make sure those are well enough separated that they won't impact each other and things like that. You need to get buy-in from all the stakeholders, that may be the users as well as the developers and things like that. And you develop your estimates so that you can have this conversation with everybody. And they initially estimated that this would take 6 to 12 months, and it took about 12 months. So they were about right on this. And so there's a couple of different approaches to these kind of refactoring exercises in complex environments. So this green box is your code at large, and the circles are modules or components or units within the code that you want to that you need to make changes to. And if these changes are kind of scattered around and fairly small, it can be maybe okay to just do them all at once and do the testing and be satisfied with it. But if there's a lot of connection and the changes are invasive or large scale, then this often gets bad results because it's too much at once, effectively. So you want to think about strategies to simplify things. One approach is to turn off all the modules except for the one that you're refactoring on, and make sure you have some way of testing those results, just unit testing level, and you do that refactoring. So the first row we've refactored from brown to blue, and the second row we've refactored a different component from pink to different blue, and there's another pinkish thing to purple. These are different things. You test them separately, and then you put them together. First you put 2 of them together, and then you put 3 of them together, and then so you build up confidence by going through these sort of stepwise refactoring and testing and building it up, right? Another approach is to take all these things and to make a very simple environment. That's actually, there is a green square there. And So this is kind of a new separate environment, simplified down so that you can take a module over and you can work on that, and then you can do the refactoring, and you can put it and you can test it, and then you can put it back into the larger context and test the whole thing together, right? Go back to the integration testing, and then you do that with another components that you need to change, and you test two refactored components together in the whole assembly, and then you do it with the third component, and you have all three that have been refactored, and you've made your change. So there's a couple of different approaches that you can take. Now, this is how they did it in the Amrex code. So, or in the Flash code, trying to adapt to Amrex. So they had, Amrex, they put the library in there, and they started looking at what requirements they had. They did this by starting out to look at a simple hydrodynamics problem that they were trying to deal with, and that had certain data structures and APIs that it wanted to use from the adaptive mesh. And so this was kind of their simplified environment. It didn't have all the complexity, but it gave them an initial look. And then they built an interface that had these iterators. They were initially designed for Paramesh, but they did an adaptation for Amrex to basically provide those capabilities. And then they added on top of their simple hydrodynamics, they made it more complex. And so they added back more features, and they refined the interface to Amrex so that they were testing out these additional features that they were turning on. So they developed incrementally this new capabilities that they need in front of Amrex to make it look like Paramesh. And they ended up with the capability to use either Paramesh or Amrex in the code, and then they could comfortably abandon Paramesh. And so to have a good outcome from a refactoring exercise, you need to know why you're doing it, what you want to get out of it, make sure that it's sensible. You need to figure out what you're going to do and how much it's going to cost. Make a plan for it. You need to make sure that all this makes sense, that all the stakeholders, developers, and users buy into this and are going to be, good with the time it takes and the impact on their own development work of other features or on other aspects of using the system or things like that. And as I think emphasized all the way along, you need to make sure you have really good testing capabilities all the way along, the ability to verify all these changes that you've made. And so there's a book by Michael Feathers called Working with Legacy Software. And his definition of legacy software, legacy software is often a pejorative or viewed as a pejorative term. His definition of legacy software is very simple. It's any software that doesn't have sufficient tests to allow you the insight to work with the code, to do refactorings and things like that. So by that definition, there's a lot of legacy software out there. But oftentimes it may be challenging. I mean, ideally, the tests have been developed with the code and you have a lot of that, but you can also go back even to code that you don't necessarily know well and develop tests if it really needs to be refactored. That's more challenging, obviously, but that is possible. But you need to do it very carefully so that you can try to make sure you have sufficient coverage and you're covering enough of the use cases to make that work. But anyway, so that's a quick story on refactoring of scientific software. So, and I think I'm just about on time. Any questions or comments?
Thank you very much. Yeah, just right on time. I don't have any questions on the chat, and I don't have any questions on Slido. How about that on the floor?
Here. Yeah.
Okay, go ahead.
Awesome. Yeah, I was just, one of the things my group struggles with, you showed on the one slide, like they estimated 6 to 12 months, and they almost made it at 12 months. And to be honest, that's something that my
we struggle with, and basically, because a lot of times at the beginning, someone asks for a specific time, how long will this take? And we find it's really hard to come up with a good estimate. So I don't know if there's, maybe for anyone, like, do you have suggestions on how to come up, like, either I can say like something I know will work like 5 years, but then like, you know, people get sad, and then or I underestimate, you know, yeah, any suggestions?
Scotty's principle from Star Trek, you know,
Yeah,
just
right.
multiply by 3 or something. So I will say I am horrible at estimation myself. I have a very hard time with this as well. So I'm not probably the best person to answer that, but I suspect there may be some folks who have some thoughts about that, and that might be a topic for discussion. One thing is just gaining experience and looking at the history. As you work together as a team on a software project, you get a better understanding progressively, especially if you're thoughtful about what you're doing, as to, you know, you're observing when these things take place, you're consciously doing refactoring and things like that, and you can observe these things, and you can see how long you thought it would take, and then how long it actually takes, and you can think about why that might have been different, and you can refine your thinking. So over time, this will probably get better. It may or may not transfer to another software project or another team, or if you have huge changes on your team, you may have to recalibrate. But that's certainly one element of it. But offhand, you know, sort of coming in arbitrarily, there are techniques for estimation, and BSSW has a blog post from Chase Million. I can look up the link for you. But he has a recommended reading list for research software engineers. He has a small company, and these are books that he recommends to all of his people, but also to the larger community. And there are 2 books in there about estimation that might be useful resources to take a look at as well.
Yeah, I'll check it out then. Thanks.
Any other questions or comments before we go to break? You guys get a little break from me. Actually, this is the end of me, so you'll hear from David and Pat in the rest of the day. All right. Thanks.
All right. Thank you very much, everybody. Hope you enjoy your break. Thank you. And we will start again at 11 sharp, so we can keep on pace. And thank you very much. Enjoy your break. Bye. Some people can't see me because I'm short.
So we're going to go ahead and get started back up again. So we're going to continue on with the tutorial series, better scientific software. And up next we have Pat.
Okay, I'm Pat Grubel. I'm from Los Alamos National Laboratory. I don't think anybody can't see me. I'm a little short here. I'm going to talk about collaborative software development. And yes, I need to learn how to use this. Okay, it's the big button. Again, our license. We're going to talk about why we develop in a collaborative manner, and we'll touch a little bit on tools. And then one of the tools that is very essential is version control. We use Git for that. And I will talk about building Git workflows, give you some examples, and think about what would be good for your Git workflow if you don't already have one, or maybe what you can include in one that you have that would help you. Then we'll talk about using Agile for scientific teams on developing software. And one of those tools is Kanban. I'll get into that somewhat. So if you haven't already started that type of process, you might be able to use that to help you, especially if you're getting started. And then we'll talk about, and David did talk about this somewhat, about the code review. We'll talk about the importance of it and a little bit about how to do it. And through all of this, there are resources like David mentioned that he put on that site, the very first slide. And all the sites are actually there, so you don't have to go through the slides to find them if you're interested in just one. And last, I'll talk a little bit about software licensing. And then at the back of the slide deck, there are some actual Git workflows that from different science projects, including I think Trilinos and Open MPI and a software project called Plexi. So you could look at those and see what some of the real science teams are using for their Git workflows. So why develop software collaboratively? Well, most teams, most projects are actually manned by teams, not individuals, even though sometimes you might have somebody that takes off and tries to do everything by themselves. But so collaboration has advantages. It can help make you get to the point where your software actually works quicker. The design is better because you're collaborating with people that have different experience levels, both in maybe the science domain and in the software process as far as the technical points. And it can even be enjoyable. I know that at Los Alamos, we have a lot of teams that are now doing tea times. And in these tea times, they don't even necessarily talk about the software. They come in with their little person, so they get to know each other. And then sometimes that migrates to actually solving problems at that time because they find somebody they wanted to talk to and they weren't able to do that. Now, that's not always possible when you're not co-located. So that's one of the challenges for collaboration. A lot of our teams are now virtual. They may be even across time zones that are across the world. So it becomes a real challenge. And so you have to have really good ways of communicating. And that even goes for those who are co-located, because sometimes people communicate in different manners. And so you need to make sure you have those channels available to them. So also collaborating, making sure that everyone is working from the same version, that can be very difficult. So you need to set up rules for that and make sure that each person can contribute equally. The other thing that collaboration can't, when you're on a team, it can become hard to understand what other people are doing with their code. So you need to set up channels and make sure that you have a way of doing that and that they understand what was intended. Okay, so there are a lot of tools. We're going to touch on some of these, and there are many more. I just threw some up on there, just splattered them around a little bit. But there are a lot of tools. And so one thing we want you to think about is what you need to use for your project or for yourself that would help. So why do we need these tools? They help us keep organized when we're working on a team, and then even our individual work, we can stay better organized with them. It keeps all the developers working on the same page and gives them the knowledge of what the work to be done, maybe what your future goals are and how that's going to happen. It helps you keep track of things like any kind of features that are requested or bug fixes. These are the types of things that we use the tools for. It also helps you capture any type of information for the collaborative process. So one of the major tools, of course, is version control. Many people talked about that in the last day and a half, and we use Git. And so we're going to talk more about using Git for version control. So it's a means of tracking your changes to the source code and other parts of your project, even your documentation and even your analysis type processes can be put in version control. There are various hosting services, including GitHub, GitLab, and Bitbucket. And but the main features of Git, I'm going to get a little basic here. So if you already know all this, please excuse me, but there may be some people in the audience that don't. The main features are branches, pull requests, clones, and forks. And so branches allow separate development for fixes on the same repo. And that can be by one person or multiple developers. And then pull requests enable the place where you can do a code review. And also, depending on your workflow, which I'll get into those, this can be a time where you can actually put up a pull request that maybe is not really ready, but you want to get other people's ideas on it. And also at this point is where you would want to make sure that your testing procedures are in a good place so that you have not only the review, but testing before you merge into a main branch or an important branch. Clones allow each developer to have their own copy on their own system, or even multiple systems if they're maybe testing it out on different platforms. And then forks allow that anyone from outside, if you're an open source project, they can fork your repository, and if they have some fix that they would like to see come back into you, they can collaborate with you on whether or not that could be put back into your main repository. But we're going to talk mostly about the first two so we can get to coming up with a Git workflow for your project. So this just shows you a little example of version control and how you'll have a remote repository, and then each developer could have their own local repository, at which would have copies of everything in there, plus maybe some of the work they've been doing. And then they can put that work into the remote repository so it's in a safe place and other people can see it. And I'm not going forward. Okay, so again, the use of branches, this enables you to have the independent development on the same repo. So you can have multiple developers developing, doing things, making new features, doing fixes, even maybe making up tests that are under the version control. And this also gives us a way of making different types of workflows. You can have protections for your main branch. And so the idea is that you develop on a branch, you test on that branch, and then it's reviewed and you make sure it works before it's merged into main. And of course, integration occurs at the merge commits. So this is just a very simple diagram of what happens. You have a feature that you're working on. You may start out from main and work on your own branch and then put it back in. And you can see the second example where the main branch might diverge as you were working on it. And then you would have to maybe, if there's any conflicts, you would have to fix them before you merge it back in. But there are times, and I don't know if it shows up, that's actually a don't do this symbol on there, but it's pretty faint. Anyway, so how do you make sure that you don't have this kind of complexity, which could be multiplied by the number of developers you have? You need to have a workflow policy. So there are some things you could look at this one and say, you should name your features with a descriptive name. Stuff A and B don't tell you anything. And then you should have some rules about where branches start and where they end. If you multiply this by several, even just a few developers, this could be very complex. And then you don't really need a complex model until you've matured and at that time you can decide what kind of complexity you need to add to it and not just throw things out there. So think about using an issue tracking system, and your names should match that in some way, and come up with some of these rules that would help you. Okay, so the other thing that you can have with branches is you can have infinite lifetime branches besides main. So if you are if your project has a release type scenario, you might have some infinite life branches that have production, pre-production names to them. You may have some a development lifetime branch where you're doing all the development and it's not as stable as main. And in this case, you can see where these issues were put into development first, and then at some point it was decided that they would go into main. And that's how you might keep a stable branch. There you can decide what to name these and what is good for your project, and it helps signal to your users what they should be downloading and using. So how do we make sure? Oh, somehow I went backwards, sorry. Okay. So here's some strategies. You need to decide what is stable and under what conditions, what tests are run on which branches, and what the rules are with those. You may have some very, you might have just some very continuous integration type tests that are just sanity checks. You may have some more rigorous tests that are done on a nightly basis, and you may even have some more rigorous tests before you put something out into production or give it to your users. So you have to come up with that. Again, you see these different lifetimes, the indefinite ones, the shorter term ones for features and fixes, and then some longer period times if you have like a release schedule, and what you're going to support. I mean, how far back do you want to go back as keeping those around? So you have to establish these workflow policies to help you with your project. So the other feature with Git are pull requests, and we use those. Those help you. I mentioned a little while ago, you could start early with a pull request so that people can start seeing what your idea is and where you're going with it, and maybe you want some comments on that. So this alerts your team and even users that there are some changes that we're going to be making, and you can have discussions about that and have follow-on commits. Or you can use the pull request to be something that you want to put in right now that you know is working, is improving your code. And even then, it gives others an opportunity to look at it and say, wait a minute, that's not what I meant by my feature request or whatever. It just gives you time to review it. At this time, you can request particular reviewers. You may want to request somebody that has the domain expertise, make sure you did what they wanted, or you may want to give someone knowledge about that part of the code. If it's a very large project and they haven't worked on that part, that might be a good time for them to look over that and start understanding more of it, or someone who's new on the project. So there's different ways you can use this reviewer request. The other thing is you need to set policies for merge, such as things for coding standards, a minimum number of reviewers. You want to have at least one reviewer. You may want to have a science reviewer and a technical reviewer. And then you can also, in GitHub and GitLab, you can set up automatic protections that only certain people can merge into certain branches. So what makes a good pull request? This one is really close to my heart. I had a developer that was working on a piece of code for a long time, and it really turns out he really had too big of a pull request. So you want to make sure it covers just one thing and that it's independently manageable. So this second point here, avoid large PRs, try to break them up to keep them small. And that goes in with the merge frequently. It helps to have, if they're smaller, you can merge them in frequently. That helps because if you have a lot of people working on the software, their branches are diverging as the commits are coming in. So the sooner you put them in, the sooner they can merge it into their own feature branch and possibly take care of any conflicts that they would have in the future. Another thing is to make sure you have a good description in the pull request of what you're meaning for it to do. And that way, both reviewers and users can look at it and see if it's doing what you claim or what they wanted, if it comes from something they requested. Okay, our next topic is Git workflows. I don't know why I'm having so much trouble with this. Okay, so a Git workflow consists of both your structure of your branches and the policies that you set up for your project. So you'd have your designated lifetime branches again. They may be whatever you come up with. You may have main, production, pre-production, development, feature branches. These are usually new features and bug fixes. And then if you have a scheduled type release schedule, then you'll have that in your policies when you're going to do that and how those tags or branches or the combination of them are named. And then you should have some rules for testing, what tests are going to be performed, and then the branch protections, as I mentioned a minute ago. So there are 3 commonly known Git workflows that are kind of general and I'm going to show them to you and go a little bit in detail into them so you can kind of decide what would work well for your project. And again, at the end, you can look at these science projects and what they use. And then Ross Bartlett, who's a member of the Ideas team, has this document called Design Patterns for Git Workflows, and he really goes into some extensive discussion on them. So it's a very good source if you want to look and see something that you could use to help your project. So the first Git workflow was Git flow, and you can see looks quite complex. It's maybe hard to see some of this, but it has the main branch and a develop branch. And this is designed for software that has official releases, and you may be in that category, so you may think about this. You can see that if there's a hot fix, it would go into both of those branches because they want to make sure that they both work. And then on your left, there are these feature branches. And like I was mentioning before, you may have to, as you're making fixes in the development branch, you may want to update those branches before they go in there. Then on your release branch, this would be probably not as long term. You may get to the point where you know you're going to put out a release and you want to make that more mature, make sure things are working the way you may be testing that in a different manner, making sure it works on all the platforms, that type of thing. And at some point, you may make a tag for that release and put that into your main. So you have to think about how you have official releases, and they use Git extensions to enforce the policies, and you can go to that site. And then you have to determine how you synchronize main and develop in this type of scenario. And the blog is on here, the site for it, if you want to look more into what Vincent Dreisen had as an idea for it, all the particulars. Next was Git Hub Flow, which was published as an alternative to Git Flow. And it didn't have a structured release schedule, so it's a much simpler workflow. And the idea with it is that it's got continuous deployment and continuous integration. So all the commits in the main branch are deployable. They make sure they're mature enough that they actually are deployed. The idea here is that you push your changes quite often. That's probably a good idea if you're working in a branch to do that. I know some people, and you need to make sure that your developers feel comfortable doing that. Sometimes they don't want people to look at their code early, but it really does save headaches if you lose, something happens to your system. And also, you could ask other people to look at it. And that case I was talking about where this developer waited a long time, that was one of the things he didn't do, and we couldn't look at what he was doing, and it became a problem. So it's good if you can get them to push to the remote constantly. And then the other idea with this scenario was to open up your pull requests early so that more people can collaborate with the developer on what they're actually doing and have the dialogue start early on that. And on all of these scenarios, usually you merge in the main after a review. So you not only have the initial and ongoing talks, but you have a code review. And the last one that's a general is GitLab Flow. It's kind of in between the two. And because it's set up for a semi-structured release schedule. So if you have any users, usually you need something where you can do this type of thing. And it simplifies the synchronization between the infinite lifetime branches. So the idea here is that your main branch is the staging area, and then the mature code in main is picked off and flows downstream into your pre-production and production infinite lifetime branches. So this allows for you to have releases that go into a downstream flow. You make your fixes and features in your main, and then decide when to deploy them and on what your schedule is. So those are the three general ones, but what do I do to decide how to establish my Git workflow? Well, some of the things you need to do are you need to communicate it to all your collaborators. And so put your workflow description in your contributing guide so they'll know what they should use. Establish the conventions for branch naming. That should all go into that contributor guide. Do you want to do it by issues, or are you going to have minor and major versions? If you look at some of the examples in the extra slides, you'll see that they use that in some of those workflows. Then you need to enforce different things. The workflow with branch protections, like I said, you could do that automatically on some of the menus. And then that would help you with limiting who can push and who can merge. And then you should have testing and review requirements. But we don't want you to think of this as a really hard process. Think about your team culture and what would be acceptable to them, what's feasible with them. Start out simple and build up. And yeah, I know that we've had discussions with side discussions with people where sometimes we have domain scientists that don't want to go along with this. We taught Git workflows. It was just Git really for some scientists, and there were a few of them that I'm only here because I have to be. But I think they've come around now to understand that this type of thing helps them. So if you can give them some things that will be acceptable at first and build up to their confidence and working with you in this way. And then you can add the complexity when you need it. So another thing that helps with your software development teams is to use Agile. And so we're going to talk about that. This fits the research experience because often we don't know where we're going. Sometimes things change and we need to be able to adapt to it. But the heavier weight approaches that might be in some of the processes don't fit well with these types of teams and with the small teams. So what you need to do is be able to be flexible, and that's why we suggest using Agile and then tailor it to your team. So this works well for small teams, and it can provide the structure that will produce all the things that we're talking about in this tutorial: productivity, even productization, sustainability, flexibility, because your requirements change as science changes, as we learn more things. And then, of course, communication is key when you're working in a team. So what is Agile? So it's not a software development lifecycle model, but there are some misconceptions. You'll hear people saying, I don't really write documentation, I don't do formal requirements, I don't design or really test. Well, we're not suggesting that they should be able to use any of the excuses to do sloppy work. What we want to do is be flexible and be able to do the things that we need to do, as David mentioned earlier, to look at the short-term goal for your science, and longer term, you want to be flexible, but you want to have those goals so that your software will be sustainable and also be productive at the same time. So sometimes they say that Scrum and Agile are synonymous, but they're not. So it's kind of like a square and a rectangle. Scrum is Agile. Agile is not only Scrum. And it's not Kanban either, but Kanban is a good place where you can get started. So I'm going to talk a little bit about Kanban, and so that those of you who haven't used it can get started with it. I may talk about it without the slides in a minute. But in the meantime, if you want to look into more about what Agile is, there's this manifesto for Agile development. And right above the red box, you see 4 lines that have the key elements. And you can see that the left side is in bold and larger print. And that's because we emphasize those things on the left side over the things on the right side, such as comprehensive documentation. The second line is important, but it's not as important as having working software. It's not that we ignore it, but we do need to emphasize working software over it. The same with your processes and tools. You need to emphasize what the individuals and the interactions are on your team over forcing to use a certain tool. So how would you get started? Well, these are not hard and fast rules. So what you want to do is adopt a few agile processes, and you don't want to look at another team and see, hey, they're working really well with that process, pick that up and find out it doesn't fit your team at all. You might want to pick a few things that you see that they're doing and see if you can do that, use them to improve your processes. And if you haven't, Kanban is a good starting framework. You can follow basic principles on it, and you can add some of the practices when it becomes advantageous for your team. That's better than taking a Scrum type process that doesn't fit your team well and trying to remove parts from it. So let's get a little bit more into Kanban. This is a basic Kanban. Usually you have columns with tasks in them. This is the very basic one with a backlog. Those tasks would flow into the ready when they're ready to be developed. And then you have your in progress and completed tasks. Now, I always like to have another one over here that shows things that were recently completed, because it's nice to see like what we've been doing just in a short period of time than having something that's really long. But the big key here is that you don't want to have too many in progress tasks. Think about what you can tolerate on your team. And you can add all sorts of other columns. If you have a personal Kanban and you're a student, you might want to have a column that says waiting on advisor confirmation to do, or you might have one that's under review. So you're waiting on that, but you can go work on something else in the meantime. You may have a blocked column, and this gives you a visual picture of what is going on with your project. And it can give it for all the team members. There are different ways to do Kanban. You can use a blackboard. You can use sticky notes. I had just a meeting where we were just throwing out ideas, and we did sticky notes on a blackboard, and then I took all the sticky notes back and put it on a real board. But it made it real fast to do, and it was just an idea meeting. The big thing again is you want to limit the number of in progress tasks, and a common convention is to use 2 times n minus 1 where n's the number of team members. And then, but each team can look at this. One thing that this helps with is in an R&D setting, it avoids deadline approach, and you can handle those in a different way so that you can continually work on things without too much worry about that. And what you want to do is optimize the flexibility of your team members and not have too much swap overhead. At my lab, most of us are on different projects, and it really helps to have these Kanban boards so I can jump from one to another and see what I was working on and what I need to work on. And also I can, any team member can say, you have me assigned to these 4 in process tasks, and I can't do all of them. Which one is a priority? There's things that you can use this for. So it provides a view to manage all your issues. There's a lot of tools, like I said. Did I get past this? Yeah, there's your whiteboard, blackboard, and then there's a lot of software tools. Most of my projects use GitHub or GitLab issues because there's a project board on those, and you can actually put your issues on them, and you can put extra cards on there if they aren't really issues. But then there's Trello, which is really nice because a lot of people use it for maybe personal Kanbans, because you can check it anywhere. You can check it on your computer, you can check it on your phone, so you can work anywhere. You might not want to use Trello if you don't want to be accessible at all times, but it's a good idea for some purposes. So the big question is, how many tasks should I have? How many active tests should I have? And there's no real single answer for anyone, but for your team, choose something. And if it gets too busy, then then back off, or if it's not enough, you can add some. So think about the go home traffic. It's usually no one's going anywhere. You're in a long line. The same thing happens with your effectiveness if you have lots of active tasks. So the other thing is to spend a lot of time consulting the board. This brings focus to what you're doing. And you can actually do retrospectives by looking at what's been done. That's why I like that little column with recently completed, because I can look at it, especially on my personal Kanban board, and I go, oh, I did do something this week. And you can use your Slack time effectively, or your developers, they might be able to go to the grab bag column or the ideas column and say, hey, I have some time to work on that right now. Or I have this in progress task that I could be working on right now. A lot of times you'll get out of the habit. That's okay. You can just start up again and make sure your team members do that too. And the other thing the board does is it does steer you towards things that you started and you may have put on the back burner that you need to get back to. So the next thing is code review. This is very important, and we have a lot of resources that you can look at for it. What does peer code review provide for your team? So it allows discussion. I mentioned that when I talked about putting PRs up earlier. It can be discussion for understanding the code, and you can actually have iterations on it to make the code even better than it was when it was proposed. You can also, at this point, make sure that the request or the bug was actually fixed and was meant to do, does what it was meant to do. You can evaluate how this new code might break other parts of your code, the interfaces, and that type of thing. And then at this point, you can also make sure that your code guidelines have been followed. And this helps improve practices. People who are doing the code review can learn from it. They could possibly, if they're a new software developer, they may learn from the review what they could do to improve what they've been doing. And also, if there's helpful coding techniques that they weren't aware of before, they may learn them. And we have the site, you have how to code review, and a pull request could be very helpful. The blog. So there's some practices that you can do that will improve your code review. Make the process formal with a structured guidelines for it. And someone talked earlier about trying to estimate time. Make sure you put in some time for the code review process. A lot of times we think, oh, I'll just make this code, and you do your time estimates and you don't think about that. That does take time, the review itself, and then any changes that might go on because of it. And I mentioned a little while ago, make sure you have, if you need it, a science review and one technical review. Make sure that if you're the reviewer, that you get to it in a timely fashion. And that way things can progress and things don't get out of sync as much. Also, two important points here. I think David touched a little bit on it when we were talking about maybe talking to a scientist or something about their code with the documentation problem. If you train your reviewers on how to phrase the feedback so it doesn't come out as a criticism of the person, it's supposed to be helpful review comments. And then you also need to train some of your developers, whether it's a software developer or maybe a domain scientist, on how to accept those comments that are meant to improve their code. It's not a criticism of you, but so these are two important points, and they're not easy. It's part of the social aspect of software development in a team. You could use automatic code review tools, but if you're doing that, you might want to make sure that you train your reviewers on how best to use them. And we have these two webinars on code review practices and investing in code reviews that could help you. And last, I'm going to touch on software licensing. I think I'm pretty good on time here. I'm not going to go into it too deeply, but we do have some sources here that you can look into, some references. But just remember that anything you write is really copyrighted, and all rights are actually reserved. Usually it's your employer or your institution that owns the copyright. The best thing you can do is specify a license so that that others know how they can contribute to it or use it. And so just treat the license as a tool. It is important to have. It's probably important that you don't make up your own. There's this open source initiative that has approved licenses for open source licenses. And then there's this tool that you could use to choose your license. And so we have those sites there. Make sure it's clearly expressed if your license is in your code repository somewhere, and easy to see. And anyway, for more information, you can see this webinar on Introduction to Software Licensing, gets into more detail. And that's all I have. If you have any questions. Oh, no, wait, I have the extra slides here, but I don't think I really have time to get into them. But they're there for your information, and you can go to their sites and look a little bit more about those projects. Does anybody have any questions?
Actually, before we get to questions, I just wanted to briefly mention that Tasia sent out an email to everybody that contains some extra information from the people running the tutorial. So please check that out. It's got some great information in it.
If you'd go to the microphone.
A lot of great information that we have been trying to apply in our scientific software setting for quite some time, where we're using a lot of Git flow with forks, and hosting forks at our institution level so that our scientists can collaborate in branches and really get the scientific process going there. But what we're finding is that we often get really stale old branches with lots of new great things in them and can't convince the scientists to bring in new changes regularly. And I'm curious if you have any suggestions on how to encourage that process to kind of keep up to date with those feature branches, get them back into develop before they're scientifically ready, maybe, or if you found any tricks, that would be helpful to know.
It is difficult when they're working from forks because they feel like they have their own repository and they don't always keep that up. So I don't know if you put out a release notes to them, or you try to keep them up to speed. If some of those teams are at your institution, if you want to let them be on the actual repo and have less privileges, that might be helpful.
Yeah, we've done this thing that we haven't really seen others do, because this whole unified forecasting system thing has many different authoritative repositories. So we're keeping forks at our institution level that aren't the main repository so that we can facilitate collaboration. We just can't quite get them on board with letting us do that update to something that may change their answer while,
Yeah, that's difficult. I haven't really come across, I don't work on something that's at that level, but I'm sure there are others out there that have experience with that. That seems like a painful thing, but just all you can do is encourage them to keep up with it. Anybody else have any suggestions on that?
Are there testing strategies that might help give people confidence that changes are being made?
So let me repeat that in case the people online didn't hear it. He was suggesting that if there were testing strategies that help people keep up with that.
We have considered setting up automated testing in our institutional fork so that we can have scientists run their regression tests, which is essentially all we have at that level, on the code that they may be using there for their changes. The regression tests are limited because they are actively trying to change the answer. So we do start to run into some spaces where, we don't have unit tests or any other level of testing to fall back on. So it becomes pretty limited in the tool set that we have for a lot of these scientific codes. Thanks.
Okay. Well, can you get to the mic? That would help.
One way that we've kind of limited that in our climate modeling system is we've actually started putting in requirements that went, because we totally understand that domain scientists are actively trying to change and improve their answer. But in the development process, we advocate, and it's becoming a rule for us, that everything needs to be behind switches. So their whole development process, even if it's fixing a bug, they might get annoyed. We're still saying the answers remain the same. You do kind of run into issues if it's you add a branch somewhere. Sometimes the optimizer and the compiler will still change the answer on you. But typically we're able to back out the same answers through reduced optimization flags, which we then use through our regression testing that tests a bunch of different experiments in our system over, like, we do like a 7-day simulation and then check the bit pattern at the end. And so it's been using those flags that has made it, and people are getting quite on board with that, even our domain scientists, and it is working quite well. It can be kind of painful. And as a technical group, you then need to be mindful of, like, in making sure you remove those flags when you update the release, which is going to update the answers. So that's just one way we've been handling that in the climate modeling group.
Are there any other questions?
I have one more comment. I'm going to be talking about testing after the break, and that kind of addresses some of these. It's a real confidence boost when you put in code changes and you see that the tests are working, and some of that can help overcome those barriers to merging code. But also I've seen projects like with AMD building software that wants to become merged into LLVM, and you have two different organizations with different goals. And in that case, you really have to look at, what are the alignment, where's the narrative that aligns our goals together as organizations, and can we track the requests and the features that we have at a high level to try and build that communication that has to happen in order to make the merges work. Trillanos is another project that has a good example of kind of a federation of projects inside of it that have been able to do those sorts of things.
Simple question, how's Git one? When I started, I was using CVS, and then first, I was like, oh, this solves all the problems. And then I switched to Git, and I was like, this is great. It is, but has it won? I mean, I stopped really watching this space. I stopped worrying about this. I'll just say and maybe Git can do this and we don't aware of it, but there's one situation where a lot of times we'll have Git repos, but we'll only need a small subset. And apparently Subversion is the tool we have to use to do that. Git itself will grab the whole thing. So yeah. So, but otherwise Git's all ours.
And I guess we'll have to take a poll on that. So we'll get to.
There aren't any questions online, just so you know. So we're going to continue on with the tutorial. We'll continue on for about another 15 minutes before lunch break, and then we'll continue it on and finish it up right after lunch.
Great. So I'm giving the condensed version of software packaging, which I condensed from a larger presentation, and I'll try and condense a little bit more. This is our normal license citation and acknowledgement slides. And in the packaging tutorial, what I'm going to go over kind of the basic steps of, as a software team, we've developed our software package. It's a library, it's an executable, it's some stuff that we want to use as a dependency in another project. How do we package that? What are the guidelines? What are the sort of workflows that we can use to go through? And I had more walkthroughs in here, but I'm just going to stick with the C++ code and CMake exports walkthrough, because I think that'll be pretty instructive. So we have kind of a mini cartoon. Sorry for the graphics resolution. I guess the image compression isn't your friend. but here's an example of a person, picking up a package with no instructions, not really sure what it does, and it turns into a Megazord or something. And this gives you the idea of, let's make sure that we document what's inside the package, how do we use it, what's expected, so that users know what to expect before they open the box, and also be aware that too much automation is not always a good thing. Why would we package? Standards and conventions save everyone time. There are programming languages that actually have as a part of their programming language built-in standards like Julia and Go and Rust. They have packaging specifications for how your software can be used as a module inside other people's software. And it helps because if you follow those conventions, you don't have to think too hard about using upstream software or packaging your software for downstream. So as I go through this tutorial, I'll give you a kind of a walkthrough that's based on a simple heat equation that I kind of did in multiple different languages. There's some, if you look at this example, there's some kind of modular design inside these files, but today I'll talk about the packaging aspect. So we start from this minimal, I've got a bunch of source code, what do I do with it? There's in here already kind of as a ground level of where do I start from? There's already a make file and a CMake lists and a build.sh, and all three of those are really great signals to people who are looking at your package as to how they're expected to build and run this. Makefile is a little bit redundant with CMake lists. It's 100% redundant with CMake lists, but it's good, when you're starting to maybe start with a makefile and add CMake lists as your packaging gets more complex. Guidelines and themes with packaging. Packaging is kind of an additive process. You want to start from something that already has a portable build system. Makefiles usually aren't super portable, but CMake lists and automake are ways to generate make files that are able to look at the environment of the machine that you're compiling on. And so those help you have kind of a portable build system that will should translate between machines more easily. Keep your source and your documentation together, because in that case, you tend to make modifications to your source and the documentation at the same time. Some projects do this and some projects don't, so it may depend a little bit on your project culture, but as a general guideline, try and keep those together. Also keep your source and your tests together so that you're able to update those at the same time. And during your pull request and review procedures, double check that your documentation and your tests have been updated to reflect what's happened in the source code. Some projects maintain separate reference artifact repositories, just as a kind of an exception to this policy. If you've got large, gigabyte files that you're using to reference the results of a run, it's probably good to keep that in a separate repository. And so your tests would then, download the reference artifact and run the tests and check. Split and separately packaged projects that become large. This is the major advantage of packaging, that once you're good at it and you are able to package your program and import that program from somewhere else, you're able to make your code more modular and kind of separate development concerns even along packaging lines. More do's and don'ts. Have a CI level integration test that is one that actually downloads and builds and installs your software and then checks the installed version, so that very high level user experience can be tested. And document the manual install process as well. Don't just release a container, even though it can be tempting. It's really good to have the steps to run so that someone can install this on their machine themselves, because people running in HPC centers don't always have all of the nice base level stuff that you can get inside of your advanced or developer systems. Another example from a couple of projects that I've worked with is they have in their documentation how to install their dependency libraries. That's important if you're dependent on something like Boost or a large finite element toolkit that has lots of configurable options. If you're dependent on some part of Trillanos, explain what parts of Trillanos and how to compile it for your users. Don't assume everyone access. Okay, I already talked about this one. We'll have access to apt-get, Docker, or VMs for getting their dependencies. Also, as you're packaging, think about what the consuming side would look like. And I would encourage you to actually package for yourself. So think about, I'm going to package this over here, but then I'm going to, import it and use it in another piece of application code that I'm writing. And so as an application code, you should expect to be able to kind of complain when something doesn't compile or install or run as expected or documented. And those are vital fixes that the developers should thank you. As a developer and a releaser of packages, you should remember to thank the people who tell you about packaging issues because they are helping everyone else who is going to use your code later. And then if you have, as you're running and using your dependencies, if you notice that there's updates they can make to their documentation, do that. It's a great way to build communication lines. And this also gets a little bit into where and what to file for bugs. When I first started in HPC, I thought, everything is supposed to work and all these people know what they're doing, but apparently that's not necessarily the case. Usually you're one of the few people who is running this code on this system. And so there's kind of a hierarchical group of people that you can involve in your compile and run and development process that kind of starts with your HPC site and facilities colleagues. They want to know what you're running. So if you run into issues, they're kind of your first go-tos to ask, what's the base system and what's the configure option there. Sometimes there are bugs that are inside of your base system that those system devs will want to know about. And then of course, if it's not, the standard contribution policy is if it's not obvious to someone, then it should be documented. And then once you have something working and you're able to use your upstreams, then definitely submit that success report and how it worked. All right, so now this will kind of go through the example a little bit. I'll have to rush, but basically once you've built your source code, you're thinking, okay, people will install this in executables, headers, and libraries. And I want to talk about how to put those, how to use the standard conventions to put those things where they go on a system when I install. There are also some ways to use the package stack to help you develop so that you can kind of install your software and use it as part of your testing. I'll just leave that as a slide that you can reference if you go to our online materials so that I can get through these things a little bit more quickly. One of the specific complications that CMake helps you with is when you have, okay, so this is actually supply chain security, and this one is transitive build link requirements. So CMake helps you with transitive build link requirements when you have multiple packages that have different maybe compiler flag options or different ways that they need to compile their dependency libraries. CMake can document how those dependency libraries were compiled so that when you build your software, you just have to think about the libraries you directly depend on and not their transitive dependencies. And another thing that's helpful with packaging is it lets you think about supply chain stability and security. So you can think about, I've released a package, now I have a commit SHA for it, and I can add signatures to my release. I can make a database of which releases I have used as dependencies and check that database in case there are bugs and vulnerabilities. You may have seen like automated announcements from GitHub, and it's looking at released versions and then vulnerabilities released for those released that have been explained for those released versions. So packaging can help you look at your supply chain security. All right, so this is the last piece of the last major piece of the walkthrough for CMake, right? So we had a CMake list.txt before. When you package your library and you want to export it so that others can use it, CMake has this great feature that is called targets. So CMake can export its target, and when you build it, when you build your software, you can say, I require MPI at a specific, right? So I require MPI at a version 2.0. And what happens is if there's a nice CMake target for MPI, then you've just imported that CMake target. I'm building a library in this case, which gives me like a heat equation solver. And that heat equation solver goes into a library that's a shared object file. And the config.cmake.in on the right-hand side. Okay, so on the left-hand side, there are some additions to your CMake list.txt that say, copy this, right? So there's install, export your heat equation targets so that your downstream dependencies can say, I require heat equation targets. And then the library will be installed, and in your dependencies CMake, they can just say require heat equation. There's also a config.cmake.in, which is another piece to this dependency puzzle This is essentially like the package config, if you're familiar with automake. This config cmake.in is run by your dependencies when they install your project, right? So there are some multi-physics solvers that are going to import my heat equation library. They're all going to run config.cmake.in that I've written here, and they're all going to check that MPI is there as part of their install process, because it's auto magic that happens when they require my target. Okay, so that's kind of the very fast view through what these CMake files give you, but this is the standard way to install a library with CMake, and I've provided some references and examples, which are the easiest way to attach this into your project. With that, make sure that I stay on time. Oh, I have 3 more minutes. Great. There's also ways to go one step farther and take your installable and compilable package and then explain to SPAC how to run your CMake install process. For now, or for just beginning, when you're starting off your packaging process, it's probably easiest to include a build.sh file, which is just the one shell line that says run CMake and use -d cxx compiler equals user bin gcc. SPAC is kind of another way to give those CMake config options to CMake. And there's lots of examples out there. SPAC is well documented, and it's simple to get started. All right, so the net result of adding this packaging here is that we've put in more documentation on how users can use the CMake lists. I should have actually put a file over on the right here that's cmake.in, but there's a cmake.in now that I explained to you is what downstreamers will use to configure themselves to use this package, and there are some tests. Write that in your README, add it in your changelog, explain how users can now benefit from the work that you've put into your packaging. Let's see, I don't have a huge amount of time left, so I'm gonna skip the part on containerization, other than to say that when you're building a container, what you're basically doing is you're starting with a preformed image that's kind of your base image. You install packages into it, and then you provide a recipe that mimics what the user does. They copy the source of your package, and they run the install process, and it builds inside of this container. All right. So in conclusion, there's a lot of do's and don'ts for packaging here. Documentation is number one. If you can document it, you definitely should. And packaging helps you interact with your users, and it's a tool to kind of couple codes and put them into modular format a little bit better. Thanks.
Look like there's any questions online yet. Are there any questions in the room? Really hungry for lunch. We are going to continue with the tutorial after lunch at 1 o'clock. So if any questions kind of bubble up during lunch, feel free to ask during that time as well. And let's give a round of applause and a thank you for all of our instructors for today. We'll reconvene in about an hour. Thank you. So we're going to go ahead and get started again. We're going to continue on with part 3 of the Better Scientific Software tutorial.
Are there more slides on this one, or do we need to switch presentations to the testing? Next presentation on testing, please. All right, so welcome back after the break, everyone. I guess I'll be the after lunch speaker on testing strategies. This talk has a condensed version of a lot of the ideas that our team has discussed and talked about for several years on testing. Yesterday, we actually heard from the Shazeb Siddiqui on the build test project, and there they had ways to run your tests. This talk will talk about what goes into those tests and how should you organize your testing suite. How do you think about a definition of done for tests, things like that. Hopefully you'll come away from this talk with kind of a renewed sense of understanding of what exactly you're testing, what should you be testing, and how far away are you from an ideal kind of standpoint on getting your code up to snuff. So let's begin with kind of a hypothetical situation where you have a science discussion and you decide we want to test out a new time integrator method for an atmospheric transport equation. It's finite volume, but uses a different way to kind of limit the oscillations that can occur and lead to instability. So of course it's conversation. How does it work on 1D transport? Maybe it preserves shapes a little bit better. So we want to actually make this thing work inside of our code and see how it will do. How do we test it? Well, we have to compare the old and the new integration inputs. We got to change the grid resolution and get timings and show that everything is as it's supposed to be. So this is maybe a little bit of a background on what kind of situation you might be going into and thinking about testing. And it's actually, Matthew Norman is a colleague of mine at the National Center for Computational Sciences at Oak Ridge. We work as liaisons with science projects that want to use the giant supercomputer Summit and now Frontier. And if you have an idea that requires 100,000 node hours on Frontier, let me know. We'd be more than happy to discuss ways to get that up and running. Okay, so what is testing? Whenever you write a code or whenever you're adding new functionality to your code, whenever you think about your designs, you're thinking about ways that you can test those designs. So you're compiling it, you're testing for defects in the syntax. When you run your code the first time, you're testing if it's doing the correct thing. And when you add things and run again, you're continuing to test. So the development cycle actually has testing built in. It's an integral part of that. But the problem is we're not always capturing those tests. We're not taking all of the accumulated knowledge that we've gathered by the hard-won process of developing and thinking about what's correct for our code and capturing it. This is not me ringing. Okay. We don't need to, okay. In-person conferences. All right, so with that, we'll go back to our example. Here's a 2D result from the new integrator method, and you have a hot front meets a cold front, and they're moving forwards in time. You get some nice structure, preservation, and conservation properties, and everything looks good. Great. Let's get the code switched over. This will be easier and faster and safer if we have the right tests in the right place. So, just getting the numerical result is not the end. The end of the process. You've got to take that numerical result and turn it into something that's a reproducible workflow that fits into what you're actually doing. So this gets us into a consideration of test and documentation driven development. You're considering new code. If you take the time to write down exactly what your motivation for putting in this new code is and what the new code will do and what it will achieve, then when you've actually gone through this entire cycle and completed it, you will now have a document that explains, when you started, how great this was going to be. And that's great for being able to show that you're checking off milestones, but also it gives you a sense of accomplishment when things are done. Once you've considered that new code, it should lead naturally to an explanation of what needs to be tested. What's the definition of this feature being integrated and working? You should implement those tests and implement and modify the code. Sometimes the tests in the code get written kind of simultaneously with the design document, and it's all part of a cycle. But it's important to keep in mind that there are those three things that are happening. It's not just writing code and running it. It's writing down the documentation and writing down the tests. And of course, there's the development cycle with writing the code and testing. Now I'll get into some general tips and strategies on building your test suite. There's a lot of different terminology and a lot of different ways to slice your source code. And so there a correspondingly large space of ways to test your code. It's good to think on two levels, and as in more long-running, complicated and complex tests you can think of as running inside of an automated or scheduled testing system. These can try and be comprehensive, almost like the academic CV that's 30 pages long. You get, an entire comprehensive picture of everything that your code is doing and where it is in performance, and it might require lots of resources, but it's important to test all of that. And then you also want to have a quick test, which will quickly diagnose errors and can be run continuously on new code check-ins. And that piece should go into your continuous integration pipeline. And having your test kind of separated this way will help your developers to ease their frustrations of the development cycle being fast and having small modular updates. For rules of thumb for a test, your test should be as simple as possible. If you have to do 100 lines of setup code before you run your test, it probably means that you have a function of a setup function that's missing from your main source code. They should also enable you to pinpoint an error, because if you have a test that doesn't actually say where the error is coming from, then your test isn't granular enough. You want to have a mix of different granularities, and I'll have a kind of an illustrative example of that later. But basically what the granularity idea is that you test with unit tests that grow larger and larger until they become integration tests. And that way you're able to kind of, if you see a test failing, you'll see it failing up the stack, and you can funnel kind of down into the bottom of where your error is occurring. You can also think about things like restart tests, or checking your checkpoint and restart process. All right, so types of tests. Let's see. So I want to start with this one. Well-known tests for enterprise software. Unit tests are the thing that verifies a single function. They're simple and they're extremely quick to run. Regression tests are where you're looking for old bugs that have occurred. Usually when a bug is reported, the first thing you'll want to do with that bug report is reproduce it. And that reproducer of the bug report makes a great test. Make sure that you save it. That becomes your regression test later, so that those regression tests are also more helpful, because if that became a bug from development mistakes in the past, it's also likely to reoccur with development mistakes in the future. So those regression tests are valuable. Integration tests are where you're putting modules together and eventually putting packages together and making sure that everything is working together. You're testing the interfaces between the modules and packages. System tests are where you're actually verifying that the software works on a particular system. And so you're pairing the software with the OS environment. And acceptance tests are kind of an industry term that's looking at whether or not, if you have a specific set of criteria that your program needs to meet, whether or not your program and your entire system meets those criteria. There are additional types of tests that we have for research software, which are things like composite unit tests that look for specific functionalities or capabilities. So you want to know whether or not your code can handle a particular science case. That becomes a composite unit test. There are also ways to verify correct behavior of interoperating functional units at different granularities. I have a picture later. I mentioned restart tests briefly before. That's where your code can restart transparently from a checkpointed state. It's important to have checkpoint and restart capability as your compute needs get larger and your job starts to require potentially more time than you can get in a single run. And performance tests are obviously checking that you're not slowing things down significantly as you make refactoring or you make changes to the underlying components in your software stack. You can also break down tests in terms of classes of tests. I'm going to call this open box testing and closed box testing. And probably the one that people are most familiar with is closed box testing, where you don't really know the internals of the code being tested. You can't modify the code. It happens to kind of a third party or legacy code. So what you do is you make an output that you trust, and you verify that that output on future runs matches the golden output that you had before. And this is a simple way of just testing that whatever's inside that box that you got from the vendor is still functioning the way that you expect that it is functioning. Open box testing is where you actually have some control over the internals of the code. You're able to jump into a module or a function and put in some assertions or insert snippets of maybe exporting some information that lets you get into the test a little bit better. All right, so let's follow through with our hypothetical situation where we've implemented a new oscillation limiter inside of an Euler integrator. We've made some changes in these yellow boxes, right? So we changed the time integrator, but we also changed maybe some details of the mathematical libraries, or we added something here. And what happens now is that there's some pieces of the code that I've highlighted in blue, which are things that you're pretty sure are still good and don't need to be retested or reworked. But then there's all these pieces in red, which if you have test cases for them, these are test cases which will give you a lot of information about the code changes that you just made. And it's great to be able to build your tests to this level where you have tests that cover each one of these different functions. Having made a change to the time integrator, you want to know that your downstreams are still working, right? So you have test cases. Ideally, you already had test cases in place before you made the change that were working, and you understood very well. And now that you've made the change, you can simply run those test cases again, get some outputs, and show that everything is working. And this is kind of showing you why having existing tests will speed your productivity in doing things with your code. You also want to think about your external consumer packages. So if there are downstream consumers of your package, you need to understand the impacts of your change on their code. So if they have tests that are import tests from you, those are good to run as well. And obviously you might need to double check your output routines because there might be some changes in output formats. Okay, so having gone through that quick testing scenario, I'll add some additional notes on good testing practices. Verifying code coverage is one quick visual way that you can use to see whether or not tests are actually being implemented for different parts of your code base. What I mean by code coverage, I actually have a picture of this even, but we had a picture earlier on in the tutorial from Pat, which showed lines of code from a single source file, and some of the lines of code weren't being exercised when you run the GCC with the code cov option enabled, or if you hook your CI pipeline into code cov into codecov.io, then you can actually look at graphical summaries of which source files and which lines and which functions have been exercised by the testing suite that you have. It's also good if you're going to be in the business of writing tests and using tests to have a consistent policy on what to do when they fail. It's great to be able to address those by issue tracking, to have a bug report that comes in specifically and explains what's wrong, and then follow through on the GitHub issue that corresponds to that bug report with what changes and updates have been made to the code to make the tests working again. It's also good to have someone watching the test suite, not necessarily someone responsible for fixing all of the bugs, but for triaging and recognizing that there is a new bug that came in and marking it as a bug and handing it off to one of the team members. I've seen really good examples of this before where a facility liaison was able to track a bug in the OpenMP stack. And what they did was they talked about the status of the code, the status of the compiler, and the status of these three different groups that all had to work together to get the bug resolved. And just by sending out this update on what the current progress was this week, they were able to get people on the same page and stay focused on what the real bug was between the three code bases. When refactoring or adding new features, run a regression suite before check-in. Those regression tests are really great for catching errors that creep in while you're refactoring. And there are a lot of vendors that will help you optimize your code. You can take your code to AMD or Intel or NVIDIA and ask them make this faster. A lot of times they'll be willing to work with you on that, but they will be very hesitant if you don't have any test suite, because they may make some changes and have no understanding of what the impact of what the changes that they've made. So having a test suite will also help you get collaborators to help you with pieces of your code. A test suite is also great to do code review before releasing. It's also good to do code review before you make a release. This is maybe worded slightly incorrectly. Okay, so do some code review before you do some code review and do testing before you make releases, because that will ensure that errors don't come out in your releases. Maintaining old releases of your code is a time-consuming process, and having good tests and code review before you release code will prevent you from having to invest that time. All right, and so I want to end with a little bit more complicated example. I've talked about, adding a new piece of code. What if I have an existing piece of code which has a very large footprint, and I want to test a small area of the code, or I want to make some changes in the small area of the code, but I don't want to implement a test suite for the entire thing because that's out of scope. This example comes from the E3SM code that Anshu Dubé from ANL was a collaborator on, and she implemented this process to actually get the piece of the code that they wanted to optimize tested and up to snuff. This is a Fortran code with lots of modules. And so the process she followed was to isolate a small area of the code, dump a useful state snapshot, because there's a lot of computations in progress. And when this module is called in particular that they wanted to update and refactor, it requires kind of a bunch of external state. And so there was a process of actually dumping that state to a file and writing a parser for it. And also there's a little bit of a source code issue, because in order for the small piece of code that she wanted to exercise to actually get run, it required some external dependencies to other pieces of the code. So some of those had to be kind of papered over so that the dependencies would work. Okay, so link-in dependencies, if there were customizations to the dependencies needed to load the state and get the test driver working, you might actually have to kind of overlay some of those dependencies. And there's a graphic of how this works. All right, so we take this small piece of code out, we isolate it, we think about the state that's needed to run it, and we build a driver which can interface to the other pieces of the code. If you have an external piece of the code, you can copy that into the driver and make the local modifications needed. The driver is then responsible for loading up the state and exercising the piece. And in this case, it's a lot of work to do this entire process, but it paid off because rather than requiring a job which took up many nodes and an hour on a supercomputer to run the test, it was now able to run in a few minutes on a developer's laptop because of the level of isolation that was achieved for this particular sub area of the code. Okay. So how to build your test suite. We've talked a little bit about this already. Use a mix of granularities, unit tests all the way up through integration tests. Think about restarting your code and ask yourself, what value does this test add? Is it simple? Does it enable me to quickly pinpoint my error? I'm going to put this rejoinder here on code coverage tools. There are many ways to get to code coverage. So there's no excuse. You should be able to find code coverage tools for your project. And as another way, kind of inside of a developer team meeting on building a strategy for testing, you can also think about this kind of a test matrix. So independently from code coverage, what the test matrix here is showing is the Flash code, which has multiple different physics functions, hydro, equations of state, gravity, particles, etc. But it also has multiple code modules, things that do the adaptive meshing or the multi-grid or the fast Fourier transform. And so what the coverage grid is doing is it's saying for every one of my tests, which physics capability is it exercising and which module is it exercising? And by going through the tests kind of from in this order of simple unit tests all the way up through complex multi-physics tests and filling in where they fit on the grid, you're able to get a visual picture of what's being tested and show kind of the developers and the physics users of this code exactly where the tests are and where we can expect to get our feedback from. There's also some gaps in here, like AMR doesn't apply to gravity, and that's an understandable thing that has to do with just the way that the physics runs. So gaps are not necessarily a bad thing. It tells you more about the structure of your code. All right, so I'm actually gonna, I don't think I have anything else other than takeaways and conclusions here, so that's it. Rules of thumb, test your tests, make sure your tests fail when they're supposed to. Have a test, not just expected to fail, but like tests that an error is returned and that the error is the error that you think it should be. Add regression tests to make sure your old bugs aren't reappearing. Test regularly. Have fast running continuous integration tests, but also if you have a larger code base that takes longer to run, have some scheduled nightly tests. This is important when teams are adding code regularly, and they'll help you identify and document where the changes to your platform, et cetera, have influenced your code correctness. Automate your regular testing, use an automation framework, rely on people who have implemented automation frameworks before. Once you put in that effort to automate your tests, then it pays back over time, and you don't have to continue to build more automation. Test your assumptions, exercise your third-party dependencies, prove that they work for your case when you're adding them in. Add tests when you join a new code, stash the tests used that you have used to diagnose issues, and think about testing strategies that are also physics-based. Look at conserved quantities and symmetries, synthetic operators, use the specifications of how your code is supposed to work. What are the error tolerances? How are these modules supposed to work together? Use those kinds of specifications to guide where your testing will fit. All right, and so with that, I'm just gonna give you one more slide of takeaways. Have a testing strategy, use automation. There's different challenges associated with different kinds of code bases. Legacy codes without the existing tests can be a little bit more difficult, and you have to be careful where you put your effort in there. But eventually you want to verify all the components if you're releasing the code. Don't get distracted by having too many technologies and focus on exercising your code. Start small and do something that works rather than try and adopt absolutely everything, because it's better to start small and have something that works. So with that, here's just a summary of the things that I covered in testing, and I'll open the floor for questions.
Thanks. It's great so far. I guess one thing that I struggle with is code coverage on legacy models. And because writing new code, you can think of ways to exercise it, but legacy models that are already tens or hundreds, thousands of lines, up to millions even. I've just never really could think of a good strategy to start figuring out how to test that robustly to get good code coverage. Because sometimes you might, or for instance, in a climate simulation, you only get into one exercise, a single piece of code once over 100 years when it gets into a specific realm. Like it's kind of, how do you really do that? You would hope that the original developer did some testing, but I was just curious if you have any comments on strategies about trying to improve code coverage on these massive legacy models that are still in development and getting improved upon. But it's, yeah, that's just been one of the big difficulties that I've had for this code coverage question.
It sounds like you might have a lot of experience with this and maybe have some of the answers. I might consider this as a closed box testing problem, where you're just going to kind of isolate it as much as you can and make sure that the inputs and the outputs are what you expect. Mm-hmm. But if you're hacking on, a piece of that code base, maybe that's the piece that you need to add the tests for the most.
Yeah, because typically that is the way we do it, is we look at the outputs at the end, we reduce it, a massive climate state, down to a single checksum, and then we use that to check the answers. But yeah, it's just difficult. I'm trying to think of how do we encourage developers to think about code coverage for testing. And yeah, but yeah, it was a difficult problem.
Yes. So one idea to approach that might be to take the way that David talked about that was used to isolate the particular pieces. And if you could instrument the code that you're interested in improving the coverage for and include that in like a Century simulation run or something like that, and identify where the code that you're missing tests for gets exercised, and then capture those snapshots as state that you can use the technique that David talked about. that, it only gets you part of the way there because you're relying on, what is exactly going in and out. So it's pretty specific, but it's at least something that you didn't have before. And if you just instrument where those paths through the code are being exercised, you might be able to identify that in the long run or something.
And we do have a question from online from Sean. It's a two-part question. So from the previous presentations on project management, adjacent techniques such as Scrum, Agile, etc., how do you budget time for testing and fixing broken tests? Or how do you convince project management to incorporate time for this type of coding? Then the follow-up is, how much time should project management budget for code coverage and test generation? I tend to budget 15% for myself, but that may not work for everyone on every project.
This is a difficult question, and I'm going to have to defer to the answer that we had earlier of kind of do these things with your team and have an estimate of how to have a beginning estimate and then track how long it actually took and use that to calibrate yourself and your estimates. 15% sounds like it could be a reasonable amount of time, but I would also caution to put together a mental model at kind of the level of a feature that you're adding rather than at a whole project level, because they're very different kinds of estimates. And so for one feature that you're adding, you might say that I'm going to need 15% of my time to get the test and the CI stuff working. And that's reasonable. But if you're trying to make a wholesale change, then that's a different kind of estimate. All right, thanks. And with that, I will welcome Patricia Grubel for our next.
Want to put up the next stock? So our final subject, it'll be reproducibility. Okay, so this is becoming a very, well, it's always been an important topic, but improving reproducibility through your better software practices. It's always been important, but it's becoming more visible, and so we'll, and then there's our license again. But a lot of times there's different terminology, and historically it's been blurred a little bit. These are some of the terms that you might hear. Of course, reproducibility, replicability, reliability, correctness, accuracy, transparency, and credibility. And they are all related, but we'll just talk about some of them. The biggest definition that we need to look at is there was a difference between reproducible and replicable between different organizations, and there's become more of a consensus on these and working towards that. And you can look at these documents if you want to know a little bit about that history. But what the definitions are is that reproducible is when another team can obtain the same results that you did using, or the author of whatever source this is, using the same environment for the experiments. Where replicable is when a team takes a slightly different environment and they obtain consistent results that may be slightly different, but you can see why, because of the actual environment was a little different. So why is this important? I would imagine most of you know why that's important, why you would want to be able to reproduce your results, or somebody else would. But here's an example of when the psychology findings were not as strong as claimed. And this was highlighted by the New York Times, and it wasn't a really good example, and it makes people doubt your work. This is only one of the examples. And in the past, computational science had kind of been spared the spotlight, but David showed you a couple examples earlier of some catastrophic things that happened. So it's very important that we can see reproducible, be able to reproduce experiments. There was a 7-year war over this example, over the supercooled water properties. And so in 2009, Debenetti said that there were, in his report, that there were 2 possible phases, both high or low. And then in 2011, Chandler at Berkeley redid some experiments, and he came out with that there was only 1 phase, which was high density. This was published in Nature, and they said that if you want to reproduce this, we'll give you the codes and the scripts. But they didn't ask for them, give them out. And so Debenetti with his colleague Palmer asked them to send the code. They didn't. They had to appeal to the publication. And then when they got that to see why they got different results, Palmer found a feature in Berkeley that was used to speed up lamps. And when he put in a more standard approach back into it, he obtained the same results that Debenetti had gotten in 2009. The resolution of this took 7 years. So, and Palmer, this quote, "There's no way you could reproduce the Berkeley team's algorithm the way they had implemented their code from reading their paper." It's very important that you have a way of people being able to reproduce or at least replicate your the results that you got. And so what could they have done here? They could have, we're going to see where both publishers and other venues are asking for those types of things. Another example is this Python scripts that used a GLOB module for these nuclear magnetic resonance data. And the dependence on the order of the listing of the files made the results different. And the GLOB module actually ordered it differently whether or not you were running on Windows or, I mean, on Linux or Mac Mojave. And so this cast doubt on the results of over 150 papers. And what could have saved us? A unit test could have, making sure the tests were run on both platforms, any platform that you think that your user are going to use this on would have helped with that. But so we have to be careful in our science software development. Again, we want to highlight our fundamental idea through this whole tutorial, which is science through computing is at best as credible as the software that produces it. So I guess we should all have that on our mirrors, right? Now there are some incentives for paying attention to reproducibility. However, a lot of times you get under pressure. I was talking to a student earlier, and we have these pressures on us to get a paper submitted. You need to get published, complete this project. And at my lab, most of the developers are on several projects and they get pulled away on one. And so they don't get to those things. So that's where your employer might value things more. They don't see all the things that you're working on that will help with this type of activity. But the goal is that we want to change the incentives to include valuing of better software, and that way we'll have better science. This is a long-term goal, and it requires a culture change. We've talked about that a little bit before. It's in the early stages. We're working on it. A lot of different organizations are working towards this. The other thing is supercomputer cycles are scarce resources. And when we're thinking about HPC and you're talking about these long running simulations, you don't want to have to run them 2 or 3 times to make sure that the results are correct. And that happens. And sometimes you still don't have correct results. So the other thing is you need to have confidence in your results yourself. You need to be able to project that confidence to your sponsors, your boss, or your advisor. And then, of course, reviewers, referees, and also to those who will be reading your publications and using your results. Need to think about how you would build this credibility without having to repeat these expensive runs. And so there are also expectations for your data nowadays. There are data management plans. Most research sponsors are now requiring these as part of the proposal. And there are times when they'll look at policies during the proposal review, may decide on the award negotiations, and conditions depend on them. And there are some support and incentives. You can see this example from that NSF on dissemination and sharing of research results. Some of the things are to publish promptly, share your data and things, the supporting material early, making sure that you still have your legal rights. And then there's the fair data principles, which that stands for findability, accessibility, interoperability, and reusability. So this addresses publishers so that the maximum use of research data can be done. And I'm sure a lot of you are deal with this type of where you can get data, what you need, and or how you can give it to those that will be using it. So you can go to gofair.us for that. That's one of the areas. Supercomputing Conference has the reproducibility initiative. They have 2 appendices, an artifact description. This has been mandatory since SC 19, and it's makes it easier for someone to rerun the computations you did, or even for you to do that. You give a blueprint for setting up the experiments, and this is largely auto-generated in the submission, and accepted papers are evaluated by reviewers. Also, an option is artifact evaluation, and this also improves the trustworthiness, the rigor, showing how your paper really has that built into it. And so you can get more details at the site. Other publishers are adding reproducibility to their requirements. ACM, TOMS, and TOMAX. Also, there's ACM badging, which helps with the recognition of what kind of rigor the publication went through. Other conferences have artifact evaluations, and we have this site here that has quite a few of them. And then there's also the NISO Committee on Reproducibility and Badging. This is a little bit more on the AC TOMS reproducible computational results. It's an option. There's a standard reviewer still, that hasn't changed, but there's an RCR reviewer assignment, and that happens alongside of the standard review, and it starts as early as possible. This reviewer knows and works with the author to get their experiments set up, and this could be multifaceted, and so the author has to trust the reviewer, the publication does. The referee is acknowledged, and they actually, it appears their report appears with the published manuscript, so they get recognition. So this is a good start on helping those in the science community to get some recognition for that work. It can be a lot of work, so it has And that also adds credibility to both the journal, to the publication itself. And then, of course, the reviewer gets some recognition too. So what we want is we want to create this virtuous cycle where the transparency and reproducibility requirements demand productivity and sustainability investments. And then those enable more. And so we get this virtuous cycle, and that way that reproducibility is based on good software development practices, and that gives us good experimental practices. So how do we improve reproducibility in our own projects? So there are 3 phases. There's during the software development, after the software development, and during experimentation, and actually after that too. So first of all, solid versioning practices are fundamental to reproducibility. If you don't know where the version of your code came from, you're not going to be able to reproduce it. So you need to have your version, your code under version control. Also, any documentation and even other artifacts should be under version control. Frequent commits help with that. I talked about the Git workflows. Often you'll have a development branch where you can do those frequent commits, and then as your product matures, you can put it into a more stable branch. Put those versioning information in your key outputs so that you can go back to an experiment and find out what you actually used. Version number, you could use commit hashes, which makes it even more specific. Might not be as meaningful to the human person, but you can get to that actual commit from that. And if you have to, you should not have to modify it, the version from the repository. It should be somewhere in the repository. But if you have to, at least keep track of it. Maintain your documentation, other artifacts, and sync with the code. David was talking about that with the test and document controlled code development. That's a good way of doing it. If you try to do it separately, or you're going to make time later, you won't. You'll forget it, or you won't have time to go back. You go back to that very first slide where other things become more important, and then it doesn't happen. Another thing is to build inequality from the start. Define following coding standards. It's not just code style, that's important, but there are other things. You need to have expectation for the kinds and extent of documentation. We talked about that with the example of the person who had too much documentation. So it's helpful to know what expected as far as documentation. Also, what are the types and rigor of the tests that you will be using? What's the schedule, that type of thing. And then again, we're back to this develop tests as you code. Write the test while the code is still fresh in your mind. If you are doing something to the code, you're probably testing it. You may be doing it manually. So write that into a test and put that in your testing system. Or you can use the test-driven development where you write the test first and code to the tests and then make sure that they work. Also requiring rigorous testing as it becomes more public. This is what Dave was talking about with your nightly tests. If something can't be put in a continuous integration test, see if you can do it as a nightly test, and then even more rigorous maybe as you're trying to put something out to the public. And what is the frequency of these tests? And what are your sanity checks, just to know real quickly if a commit is going to be good or not, that type of thing. And then practice peer code review. You could do it per commit. That might be those you should be able to, every commit should meet standards and be understood by the reviewer, or at least at a pull request point, some point in the process, make sure that it's you go through the peer code review to make sure that you have quality, that things are not breaking in another area. take a retrospective, or if you have a lot of unreviewed code, we've been asked about that a lot today. So you can break it into parts and do some of it. You can look over at what isn't covered and pick out parts, maybe isolated as David suggested. It's easy to say who one of them is because I'm not going to get it wrong. They do, but they might, but I don't. So, no, David Bernholdt did suggest that. Other things during development, make sure you understand the numerics of your code. I think we have the talk after this is on that, so that'll be interesting to listen to. You have, of course, floating point numbers are just approximations. So you need to be able to do analysis on what's coming out of that. And a lot of these methods have their own quirks. So you need to understand that or have maybe someone that's a domain scientist help you with that. Of course, if you're using reduced or mixed precision computations, try to compare it with the full precision version, either on paper while you're developing the algorithms, or maybe you can put in a path that will do this when you can, so that you can compare those results. And then also you need to consider the effects of non-determinism and concurrency, especially with all these different runtime systems that we're using for the concurrent calculations and putting things on GPUs. Those types of concurrency can cause results that are different because things are being done in a different order, possibly. So it could be that you might have to have an option that actually forces this deterministic computation, and then you could have some type of testing and verification method that that your results are coming out correctly. But one run may not do that because concurrency can change the order every time you run it. So you may have to force it in certain areas to run in certain orders. Know your error bounds and develop tests against them. I think David talked about this a little bit. And then consider, again, talking to your subject matter domain experts and get them to help you with it. I guess that last point is you might not always want to make assumptions that you know exactly what's going on in the domain. After development, of course, testing. We talked about testing a lot, but it's very important. Add regression tests when you fix a bug. Again, at this point, you're usually looking, you know what you want to do to make sure that bug doesn't, that bug has been fixed. So at that point, that's when you could create a test and put it into your regression testing. You can add more tests. Think about the corner case and the common case. Think about the person who might misuse it unintentionally or intentionally. I had a person walk up to me and tell me, I can break your software. And I'm like, is that your job? You know, I don't know if you could prevent him from doing that, but I did let him know that that wasn't really his job. But if he found any bugs, please let me know. Think about synthetic tests, using synthetic data. How can you exercise your algorithms with that? What about low-cost tests? I'll talk about some that can always be on in a minute. But if you have some that are not stringent and don't cost you a lot, maybe you could have those on all the time. And then do you know if there's any silent data corruption? David Rogers talked a lot about testing your third-party dependencies. You need to know what the tools are doing and if they're doing what you expected them to. What happens if their version has changed? You need to decide when you should incorporate that and when you should upgrade that. And David Rogers also talked about testing tests, make sure they fail when they should, and that they're putting out the proper error message so you can find out what happened. Thoroughly verify the code. Does it do what you intended it to? And does it do that on all the platforms, like that example, just between Linux and Mac? Will it run on all the platforms correctly that you are now starting to run on? This is becoming real important as we change to different types of GPUs and different clusters, and you may be running on multiple ones. And then test regularly and document where the changings, what happens when you change an underlying platform. If an error creeps up, make sure you document that, or any kind of behavior or result. That could be from a compiler or a hardware architecture, or even if you're using a new concurrency runtime. Okay, then you have to consider, I believe David went into this somewhat on the physics or your math-based testing strategies. Use synthetic operators that have known properties, and then you can look at the different things that are important with that, such as spectrum and rank. What are the invariance principles for translations and rotations, whatever you're doing in your model or your simulation or other types of scientific codes. What are the physical and mathematical symmetries? And then, of course, is it adhering to the conservation rules for your particular software? Here's another little thing to think about is contract programming. You could build this testing into your routines. This isn't really to replace other testing. These types of things can be always on. So every routine can be thought of as a contract between the caller and the callee. So what does the routine expect as preconditions? What are the inputs? If those are improper, make sure you have a way to guarantee that. If those preconditions are not satisfied, then the routine should return an error. And then what are the routines guaranteed at completion? You could have some low-cost tests for the results from known preconditions for that. You might need to be able to switch these type of, if the tests become expensive, you might want to include something where you can turn them on or off, so that maybe during certain testing cycles you have them on. Or if a routine is changed, that one goes on for a certain test, that type of thing. So make sure that okay, so with these routines, they might be reused in another context, and so that makes that very important. Or they might be used by somebody who's not familiar with them, and so they actually use the wrong kind of inputs, or they expect an invariant to change and it doesn't, or somehow they change it by changing that, and you have a test that says, wait a minute, this value shouldn't have changed. Seems like I had this already. Oh, I hit the wrong button. Okay. Also, you need to know what you're going to do in an experimental campaign, why you're doing it, and how. And so you need to plan ahead, make sure, especially on these really expensive campaigns, make sure that you designate one person to coordinate it if it's a large effort. That way, one person is the key person for everyone else to go to. You need to know what you need as far as your code, your inputs, your outputs, what you're going to capture and analyze, and how you're going to process the results and how you're going to analyze them. So you want to know what to expect. It's really nice to know if you have a long campaign, how long it's going to take. Will you need to have checkpoint restart, that type of thing? And then how are you going to convince yourself and those others who are that it's important to, that the results are good and trustworthy? So one thing you can do is to build confidence in this type of, especially in a large campaign, is to do some scaling up. So you may start with some smaller scale tests and scale up and see that, yes, it looks like it'll take a certain amount of time. and you know how much it's going to cost, and you can kind of judge by that. Also, you need to ensure that you have the resources to store and analyze your data. How much can you afford to archive? So what are you going to archive that would fit in those spaces? What can you process and delete to make sure that you fit into those spaces? And then what do you need to process during execution? Some tests require that, quite a few that might be live streamed, and you have to actually see what's going on. During the experiments, you want to know that you can reproduce the code that you used for each and every experiment. And can you reproduce that 3 years later? So did you keep track of that in some form? One thing that would help is to use only well-defined versions of the code, use official releases or tags, and you don't want to just say, oh, I used the main branch. Well, that's often changing, or the develop branch. Those are moving targets. So you want to pin down what you actually used. And if that's in the output, that helps. Make sure that the code that you're building is actually in the repository. Don't change versions during a related series of experiments. There may be a time when you see that something has to be fixed and you have to do it, but make sure you keep track of all that. And make sure you know exactly what changed, and then capture the exact version used for each experiment. Use only versions of code that have been thoroughly verified. That's very important. And then use regular testing to identify changes that are due to the underlying platform. We're talking about anything that we've seen compiler releases with optimizations that change the results. So we need to really keep track of what you're using. And that goes back to when to decide to upgrade also. So you also should probably keep track of the versions of your key libraries and compilers and any other dependencies that are used to build the code. This isn't done very often in practice, but it's a good practice to start. So also during the experiments, be thorough in capturing provenance for what you're doing during using all the codes, the inputs and outputs, the transformation you're using with the code, capture the code version, all inputs and configuration for each experiment. And one thing that we haven't talked too much about in here, at least I don't remember talking about it too much, is, well, one thing that helps is having the systematic directory and file naming convention, so you can find the results. But also separate written notes, either electronically or handwritten, especially when there's any manual or human interaction should be taken care of. And then use scripts to orchestrate these experiments. And if you do, version those and capture them. And then you can even have version control for data if it's not too large. Capture all your important outputs that you can. After experiments, you want to continue provenance capture through the analysis and reduction process. So again, you want to capture codes that you use, any inputs, outputs, and any transformations that you might perform on the data. Script as much of that as you can. Scriptable tools are preferred over human interaction. And if you do that, keep them under version control. Then document the process, and that's separate from your scripts. So again, paper or electronic notebook, especially when you have human interaction. And then capture your key intermediates. The more you capture, the more evidence you'll have to help you find problems that occurred later, and also for verification, if anybody wants to see what you did. Capture the data in a machine readable form that you use to producing your graphs or tables. This is expected by most of the data management plans, and many publishers are now requiring it. There are some tools to help you with reproducibility. Quite a few people have talked about containers to capture the software. That's one way. And then there's resources for understanding floating point math. This floating point analysis tool is one place you can look. And like I said, there's a talk about that after this. Also, you can use the cloud platforms for publishing code and data, such as CodeOcean, and then DOIs for code data documents at Sonato and Bigshare. Make sure that you understand those tools thoroughly before you use them. Capture something that's really important. Make sure your team members understand how to use them. So in summary, again, the credibility of your science comes from the credibility of your code and your process. And science stakeholders are ratcheting up their expectations for the reproducibility. And you can use strategies that I went through for all the phases during and after development, and both during and after the experiments. This amounts to better software development practices, and that's what we're talking about here. We're trying to improve productivity, sustainability, maintainability through these practices. And there's some other resources you can look at, and these are on that resources site too. So are there any questions? Any questions?
Yeah, we have a lot of time for questions or discussion.
Yeah, and if you have any questions over, I can go through the summary and then we can have questions over anything that was taught in the tutorial, any more discussion that anyone wants to have. I think we've had quite a few discussions during our breaks. And if anyone wants to bring up any of those points, that would be a good time. So I can go through the summary and we can do that. I think there's a summary, is that a summary? Yeah. Here we go. So again, write it on your forehead. Science through computing is at best as credible as the software that produces it. So we covered many topics from designing, collaborative software development, refactoring your software, packaging, testing, reproducibility. And there are many more. We couldn't get through all of them. We only have so much time in a day. Continuous integration, all sorts of issue tracking. If you have any questions on those, we can even talk a little bit about those. There are other topics that are important. We just don't have all the time. We do a full day tutorial and we had to kind of cut it down somewhat, but there, even with that, we could go on for a week probably on some of these things. But you're a researcher and you can't afford to spend all your time on software engineering. Your employer might not want you to. You have other things you have to get done. So what do I do? Well, again, David went through this. David Bernholdt went through this on the PSIP process, which is take some part of it, see if you can pick a process that would help you. You may spend a little bit of extra time on it, but it would help your time cost go down. So pick one, work on that. And then as you get better at that, maybe you can pick another. Again, we have the rate your project assessment tool. Take all your team members to go through it. It doesn't take very long. You could maybe see a common pain point that you know you could work on pretty quickly. And then that card catalog has examples. You might even go through there and pick something that you know would help. That a process that might help you, or if you have one, you can go through there and find what someone else did that was beneficial to them. So again, work on that. And then when you do get something done, celebrate it and go on and do another. We have the Better Scientific software site that has a lot of resources. And I'm sure that some of you have some resources that you think would be good on there. It's a community site. We'd like to see contributions to it. So if you have ideas, you can jot them down, or if you come across some tool that helps you or some process that helps you, we can put that on that site too. And I think that's about it. If you, we do have, you can write to us at this site here, or email. And again, all of the resources are on the tutorial site, and there's past tutorials on there. And then we have the ideas productivity site. We have an announcement and the monthly digest. If you'd just like to see what the new things are that are highlighted at the Better Scientific software site, and an RSS feed. So if you have questions, let me put that one back up, because if anybody wants to jot it down, but it is on that bsswtutorial.github.io. All these sites are on there. So if anybody has any questions for anything we talked about today, it is that time of day.
So I'd also appreciate feedback. So we had to comment early on that we aren't talking so much about the experimental and observational types of applications and things like that. And there's certainly other things about our tutorials that could be improved. So we hope that you've gotten something out of this, but we'd also very much appreciate your feedback and how we can improve things, topics that you think we should be talking about. You know, sometimes we have a material we didn't present, but sometimes there's new things that we haven't really thought about or developed content for yet. So all that kind of stuff, I think, is fair game. You know, how we can, if you've gotten through some of this and you have thoughts already on how we can do a better job of incorporating experimental and observational scientific work into this, we would welcome that kind of thing too. We're happy to talk with you offline. So anything goes at this point. And I think we have plenty of time because I think we're going into a break. So
would you like to repeat that for online participants?
I was hoping the mic would pick that up.
I don't think so.
Okay, so I'll let David do that.
Yeah. So sorry for folks online. We're interested in feedback of all kinds. So in addition to questions, what could we improve about the tutorials, topics that you think we missed talking about, things like that. And we're happy to have that conversation with you now or offline in whatever format is useful to you. So thank you. Please.
Remind us how we book one of these tutorials for you to come tell our scientists this.
So there's an email address there that you can reach us at, and we can try to figure out a time and place and topics and things like that. So we do these at conferences. If you happen to be at ISC in Hamburg next month, we're doing a half-day tutorial there. And we're going to be putting in a proposal to supercomputing. So those are a couple of likely options, at least coming up, but we can also do for particular projects or groups or things like that. I was a couple weeks ago at the Laboratory for Laser Energetics at Rochester and gave them sort of a short 1-hour mini tutorial So there's lots of different ways we could do this, and we're happy to just reach out to us at this email, and we'll figure it out.
That comes in a variety of links and topics from 1 hour to.
We could
multi-day.
spend days
Oh.
if you wanted. Depends on your stamina.
I have a question for the last two speakers, and it's about testing. So you introduced a lot of great strategies for increasing test coverage. And my concern is, maybe this was already covered in your discussion, but is there any notion at all that too much testing could actually be a bad thing? When we're dealing with all these different special cases of both successes and failures, when we're trying to prepare input data and compare very, very complex data structures that we expect as a result, our testing code can become immensely complicated. So I'm wondering, is there a point at which your assertions are good enough and you shouldn't move on? Or should I continue to view this as a monotonic relationship such that all the more testing code you introduce is always a good thing?
Yeah, so there's also this trade-off between testing and release productivity. So there is such a thing as too much testing, and the way that you can tell that you're spending too much time on testing is that you're not able to make progress on your actual goals and deliverables. So you have to have this balanced view where you're testing enough so that you're sure that what you're releasing is what you say it is. But you also don't want to spend time developing tests which are just because I want to increase the code coverage metric, or because I want to test this piece of code which I may use. Just like when you develop features, you develop features that add value. Tests add value to your code because you have confidence that what you're releasing is what you say it is, and you're not going to have to go back and fix those bugs. And it also allows you to check things as you add code. So the best time to add a test is when you start working with a new feature, because in that case you have the ability to test at an easy level, and once you have kind of a very complicated software stack, it may be getting away from you and difficult to put tests in there. So there's that constant trade-off between testing and productivity.
Can I add something to that? So is this mic on? Okay, so I think there's a really useful backup strategy, which David talked about, which is regression tests. So you have a set of tests, and it may not be 100% complete. It may not test every possible input or whatever, but you need to move ahead. Then somebody comes along and finds a bug, and you diagnose it, and you figure out the problem, and you fix it. And you add that to your test suite. And then not only can that bug not creep back in, but you're also expanding your tests based on the problems that have been experienced by actual users. So it's a kind of a guided test enhancement kind of strategy. And that may also, depending on that, the nature of the bug, that may lead you to think about a few other tests to sprinkle in there that are related to that, to help improve that space or something else that might occur to you. So it doesn't, don't necessarily have to do it all at once, but be ready to respond when new bugs do crop up.
And I have some more specific comments on data structures. I'm a big believer in having complicated data structures because they take away from the complication of your code. But at the same time, you need to have frameworks and conventions that allow those data structures to be composable, testable, modular. YAML has been really amazing. There are toolkits that work with YAML structured data and can verify it. There's JSON schemas, which were kind of the earlier tools, but and YAML and JSON are pretty much different formats that give you the same basic set of functionality. But then there's also something called Pydantic for Python, which is a really good design principle to use for explaining the types that should go inside of your code. And having kind of verifications at different levels of those data structures is important. And I could go on for a little bit also about the security flaws that can creep in if you don't have very well-defined data structures. But suffice it to say, verifying your data structures is a great idea.
I think one thing that should be emphasized is when you are coming up with tests, they should also adhere to the same software engineering principles that you're trying to apply to your code. For instance, I did have just the other week, I actually just deleted a whole testing directory because it was hard coded, all the paths, like had hard coded variable names. And so it was failing tests just because I refactored the code to be better. And it wasn't, and it was like, obviously the better way to do it would have been to spend the time to update the tests, but that wasn't on, it was just basically failing and non-operable for months. And there's also another thing that no one noticed. And so it showed that testing had become orphaned. And so you need to kind of still apply into the same principles. Like don't have hard-coded variables and nameless names in your testing structures, because then when you just change a nameless name and it fails. So just things like that, I think it's worth considering.
And also to actually look at the output from your tests. see if they're all failing for a month or so.
Yeah, exactly. Just on a runner that I didn't notice.
One of the issues I've sort of run into with testing isn't testing per se, but more error handling, in the sense of if folks will give me code and it'll have a test for it and it'll say 100% code coverage, but there's no error handling inside. So it's just, they only give it basically the success thing and never give it a failure. So how do you emphasize not just testing, but also that, you also want to implement error handling for weird situations. But at the same time, you also don't want to overkill it, because it's impossible to think of every possible thing that someone could throw at a function or a subroutine or whatever. So I guess how do you, I'm trying to think of I was debating to come up here because I couldn't quite formulate my word for my question, but essentially how do you emphasize that you need error handling as well as just, testing the code that's supposed to work? Does that make sense?
Are these errors that are supposed to be handled by users of your code, or errors that are supposed to be somehow cleaned up before the users see them?
Oh, it could be both. I mean, so the one example I'm thinking of is more on the user side. So you imagine they would send in a name list and we would parse it. And, you can imagine like, oh, they threw in, it's supposed to be a string, but they threw in, numbers or special characters or whatever. And so, you want an error handler to say like, hey, this is a question mark and I'm looking for a letter. But the problem is, I guess the test that came with it didn't catch that, because it was just saying like, oh, did the string pass in and it was successful, so we're done. And then I guess there's internal ones as well, but those are almost, I guess those seem like they might be a little harder, because hopefully it would have been cleaned up before it got to the internal thing. Maybe not, I don't know.
So are you also asking about, for example, where people are using other libraries, say MPI, and they're not checking the return codes from those calls or things like that? Is that
that's another example. Because they'll run a test, and if it's successful, but then you never it's just because they're not checking for it, or it'll die horribly if it's really bad.
So from a security perspective, you want to reject all input that is invalid. There's a little bit of a kind of, there's There's a maturity process to that, though. You can have kind of an error handling I've detected an error that's kind of the simplest entry level. And, at the very high levels, you might be able to provide some diagnosis and resolution and recovery from the errors. But just as kind of the base level that you should be targeting, you should know on every code that has a potential input that you can't control, whether it is an error.
Yeah, I would add another thing to think about, especially with library calls and things like that, would be what are the potential consequences if the error goes unhandled, right? So if you think about whether you're catching errors or just letting them fall through, is it, what's going to be exposed to the user if that thing fails, and are they going to get an error message that will allow them to do something about it? Or is it just going to be some mysterious thing that turns the user off or says, this software is crap or whatever, right? And yeah, I understand the pain of testing all the return codes and trying to do something sensible about them. So you might triage by saying, well, what are the consequences if this fails? And how would users be expected to deal with it, or should they be expected to deal with it, and things like that. Maybe use ideas like that to help triage. And I think the same could go for inputs and things like that, right? What's the potential danger or dissatisfaction from the users?
And also putting in checks when your code has gotten into a state that you didn't expect. You should immediately, quit and say why you quit, because otherwise you won't be able to fix it.
I think that's key, especially the development cycle. Like, don't forget about cert. It takes a lot of time to think about all the ways the user might put input, but it's pretty easy to insert routines in to a certain input. And yeah, it may not present the user immediately, or you put a question mark, but the developer will look at it.
Any other questions? Let's thank our instructors one last time. We're going to go ahead and start our last break, and we'll reconvene at 3 o'clock.
And talk about future direction for those tools as well. Next slide, please. So the problem we're trying to solve is several, actually. On the one hand, users frequently request a lot more memory than they need on our HPC systems. And that really negatively impacts batch scheduling, particularly on compute nodes where maybe the cores are shared. So both cores and memory are allocated separately or in concert. And secondly, I would say that even experienced software developers sometimes can have difficulty predicting memory application usage. And this is becoming, I would argue, increasingly relevant when complex software stacks are being used with external libraries or perhaps more asynchronicity, things like that. So I think both of these issues are exacerbated in part by a lack of simple tools for profiling memory usage. And so that's what we're going to talk about today. The primary goals then are to update and enhance a tool that we have called peak Memusage here at NCAR. Sorry about that. And what this does is report and optionally act upon application memory usage. And the secondary goals are to actually explore a little bit of SPAC package recipes and learn a bit more about the Linux linker. And actually started with both of those at the bottom and then inverted this to come up with some extensions, which we're going to talk about today. Next slide, please. So Scheduling, we often think about in terms of CPUs, but for machines such as Casper here at Cheyenne, Casper here at Cheyenne, we schedule both CPUs and memory. So it's important that you ask for both and don't exceed one versus the other. For a machine that allocates individual CPU cores, you really need to match these. If we go to the next slide, I'll try to motivate a little bit. So a typical FIFO scheduler, right? First in, first out, you execute tasks in the order they're received. A backfill scheduling, which of course all HPC systems really rely on, requires reordering the tasks based on the resource requested. So that's the ideal state. If you have a good match between needs and requests, you can reorder and disable your resource requirements. Next slide, please. Of course, what's the difference between theory and practice? In theory, there is no difference. In practice, there is. So I think it's best illustrated by these couple of XKCD cartoons. Ideally, the users are requesting exactly what they need. The backfill scheduler does its thing, and life proceeds in heaven. Life's always great. You're at the high score, and life proceeds smoothly. Reality is somewhat a little bit different. Hell. Level 1, score 0, and it just keeps getting worse. And the users don't make things easier on us, as we'll see here in the next slide. So the theory, of course, requires that users request exactly what they need. That's fairly easy for CPUs. It's a lot harder for memory. Often we observe in practice that users just either go with a default or they increase way more memory than they actually need so that they don't have to worry about it. What you see here is a histogram and a CDF of the memory used versus memory requested on one of our high throughput computing queues. And what we find is that fully 75% of the jobs run on this system use less than 10% of the memory they request. So why is that, right? And even the best scheduler is not going to be able to do much with that. So I think at least in part, it's because of a lack of good tools. So that brings us to the talk today. Next slide, please. Okay, next slide. We talked a little bit about Git in some of the earlier sessions. This tool is hosted on GitHub if anybody wants to play along after the fact. I've tried to include a number of examples that can be cut and paste directly. You can pull it straight off of our in-car our GitHub account. Next slide, please. The application is it's a mixed language C, C++, and Fortran utility managed through Git with an auto tools build system. Not important the steps to build it, but if you were to run these as specified, then the code examples that we'll demonstrate here a little bit later would run directly from the slides. We also include this tool on Cheyenne and Casper in previous iterates, and the tool as presented today will be available on the upcoming Derecho and future iterates of in-car software stack as well. Next slide, please. Okay, so peak Memusage goes back a while. I think it actually was put together in the mid-2010s. It's a very simple tool that provides users the high water memory application or memory use for their CPU memory usage from an application. So in this simple example, I've got a thread-based OpenMP application that allocates some ints on each thread. That's what the console output would look like if you just ran this straight away. If we go to the next slide, peak Memusage is very simple. You simply prefix your application binary with peak Memusage. You get very similar output. The important part is the last line there. The host summarizes, uses 81 megabytes plus a couple megs of overhead, and then summarizes the exit status. So this is what we started with several months ago. And to be perfectly honest, it existed in an old make system. We wanted to deploy it through SPAC, have SPAC do all the modules for us. So I decided to rewrite it with an auto tools build system. And then once I got inside, I realized there's a lot more opportunity there. So that's what we're talking about. Next slide, please. The code is MPI aware, but in a very simple way. It will correlate output by MPI rank, but it doesn't actually depend on MPI to build. And there's a lot of good reasons for that, which I'll try to describe more as we go through. So if you run this tool under NPI exec, for example, on 4 ranks, you'll get the same output correlated by task rank. So nothing too simple, too complicated, but useful for NPI codes as well. This is a somewhat contrived example to create memory imbalance between the tasks, but you can see it's reported accurately. The way it does this is quite simple. Next slide, please. Within the code, there's basically a static map. We infer the local NPI rank by one of several environment variables. And I think there's something like 6 there, 7 there that have been determined from different NPI installations across different machines. So it should work for OpenMPI, MPitch, and VAPitch related MPT, things of that nature. If you come across an NPI that's not accurately detected, love to hear about it, and we'll add it. It's real simple. Next slide, please. The way this works is very easy. It takes the original application binary and then encodes that inside a system call. It then uses the Linux API get usage to query the resources required by the application. And so that would include peak Memusage itself. And then of course, everything invoked through the system call, which is the user code. It's a somewhat portable, at least across Linux and Unix, or Mac OS and Linux. It works on both. One fun note is that Mac OS reports in bytes, whereas Linux reports in kilobytes, but as long as you're aware of that, easily to work around. But notably, get usage is limited to the peak CPU memory used by the application and child processes, which will have implications as we move forward. There's also really no performance penalty for get usage because it's information that's in the kernel anyway. You're just making a call into the kernel and it's reporting a couple of ints for you. Next slide, please. But that's obviously pretty limited. We wanted to extend this in a couple different directions. One was to provide similar functionality on GPUs. Probably more importantly, or more complicated, was to support a time history of application memory usage when desired. And I find this particularly important when you have multiple layers of libraries that are all operating asynchronously. It can be difficult to know or even predict when those memory profiles are going to collide in time. So I wanted to be able to extract a time varying history, particularly important for things like AMR applications that may have a very, very dynamic memory footprint. And then once I got into this a little bit, I realized there could be some situations where it's useful to take action based on a particular memory event. One of the more obvious ones for our users is if you exceed a certain threshold, you might want to outright kill the application. The operating system will do that eventually anyway, and it could be beneficial to know when you've exceeded a threshold. But following on some of the conversations from yesterday, flops being free, caching versus recomputing, you may have a data cache that you want to clear if you become under memory pressure. And so with something like a user specified function callback, you could implement something like that with this tool as well. So those are the goals. That does introduce a number of complications and design decisions, obviously above the original tool. One is we do want still to maintain maximum functionality without requiring recompilation. There's lots of times where we have a user code and we just want to be able to instrument it without going through their build process. And so we want to maintain that functionality. We want minimum dependencies for the ease of deployment and to encourage adoption. Part of the reason for that is, to some of the previous conversation, having a Fortran developer telling them that they now need to link with C++ main in order to get this functionality is probably going to get somebody not to adopt your tool. So I want to keep this as simple as possible. Also found that, of course, get usage is going to be insufficient for examining the time history of the CPU. It only reports the high water mark, and it has no knowledge of GPUs. So to address a lot of these issues, came up with another tool. It's a library in this case called log Memusage. And it's a shared library that can be linked if you want. And there may be reasons to do that, which we'll talk about, or just injected through LD preload. And functionally, it spawns a monitoring thread that polls the GPU or CPU and GPU memory if you have a GPU available. The way it does this to get the time history is it'll use NVIDIA's NVML when available. And there's also a couple of files within the Linux proc file system that you can get the instantaneous roll up of your application memory footprint. And so we parse those as well. Because we want to be able to do this without requiring relinking, and any knowledge on the user code. All the control is through environment variables with sensible defaults. Next slide, please. So what that looks like in application now is rather than run under a binary, we in this case simply inject the library through LD preload. We get very similar output. The overhead is missing, although in putting these slides together, I realized that it's easy to put back in, so I will probably do that in the near future. The same approach works under OS X, of course. You have to use different syntax, but the approach is the same. Now, there is similar functionality provided by a tool developed by Google, gperf tools. If you're interested in lightweight profiling or dynamic memory management, I'd highly encourage you to have a look at that. It also includes heap profiling, CPU profiling, and some memory allocation, some memory allocators, which can be good for performance for certain applications as well. But as we move forward, those feature sets start to diverge. So it's not necessarily a duplicate of what we're talking about today. Next slide, please. The first environment variable that controls the output is just verbose output. So if I set that and rerun it, everything in bold here, these are environment variables currently within the tool that will affect the behavior and their default. Next slide, please. We'll talk a little bit more about the ones in red on the following slide. Can we go back one? It's working. Let me try this for a little bit. Okay, so the ones in red we're going to talk about in a few more examples. Log file. By default, there is no log file. You can turn it on easily enough. What that'll do is create a per process under MPI or per rank output file with a default file name that you can control. The other two variables are polling intervals, and we'll see what that means here in a second. Lastly, NVIDIA's NVML is invoked, but it's invoked through the linker using LD open. So one pet peeve I have in working with GPU codes is trying to run them on CPU hosts that don't have a GPU can be a real pain. Wanted to avoid that. So we don't actually link with NVML. We just load it if it's available. Everything runs fine if it's not there. So manipulating some of these variables in some more complicated examples. In this case, I'm using NVIDIA C++ compiler with their standard parallelism offload in two different functionalities. So the first case, I'm going to create a test case that grabs grabs a 500 million ints, creates sorts them and makes a unique array out of it. Runs it in serial on the CPU, on multi-cores on the CPU, and then uses GPU offload. What's different now is you can see that on the host I'm running on, we've actually found 4 NVIDIA A100s. What's missing in the braces there would be the PCI bus ID. This system didn't want to give it to me, others do. I'm gonna go look at that in a little bit. And then the very last line now, you can see that this process is reporting the peak memory usage on the CPU and the GPU. I'm running this example only on CPU codes, so that 563 megabytes reported on the GPU is somewhat of a baseline. We'll see that here in a second. Running the same example instead using the standard parallelism GPU offload, results are very, very similar, but now we can see that we've used nearly 7 gigabytes of memory on the GPU with a considerable similar reduction in CPU memory usage. The other thing, which it's not really the focus of the talk, but what took 6.7 seconds on all the cores I had available on this machine on the CPU now takes 0.8 seconds using all the cores on a single A100. So that's a nice win. The time history log files were enabled by setting that logging parameter simply equal to 1. This is what a sample of 1 would look like for the multi-core CPU result. First column is simply time stamp since the application was launched. The remaining columns are the memory usage of the CPU, and in this case, the 4 GPUs that are available to my application. What you can see in those last 3 columns that are all identical is what I mentioned, that the GPU is basically pegged at 563 by, even with nothing active, it's basically the tare value. You can also see though in the bold column on the CPU, the desired behavior I was looking for. You're getting the up and down on the CPU memory usage as this application goes through its dynamic memory profile. The two parameters that control the logging frequency are first off, how often the system is polled itself. So how often this P thread is polling the system for its memory usage, and then how often we want to write that to this output file. I will add that the output file actually gets an entry every time a new maximum is achieved. So in that regard, you're always at the rate of the polling frequency anyway. You will see new maximums as they occur. You don't have to worry too much about how frequently you've requested the output to be written. Similar results on the CPU, on the GPU. In this case, this was the second example where we're now exercising GPU memory offload. Interestingly enough, I have 4 GPUs in the system. I'm offloading to 1. NVIDIA kindly picked 1 for me by default, even though Creative Visible Devices had access to all of them. We can see a couple interesting things here, I think. One is that just tapping into this feature took 400 megabytes of memory. The first 40 seconds of this application are CPU only. So just using the memory, the managed memory standard parallelism GPU offload had some memory footprint, which was nice. But similar behavior is observed on the GPU. We can see the time history of it. And every time we encounter a new maximum, it is written to the log file as well. So reasonable question would be, what's the impact? To characterize the performance impact, I took my laptop, used all 8 cores, and loaded them up with a finite element simulation. In this case, it's a triquadratic, so third order Poisson solve using the finite element method, using all 8 cores. So the idea was there should be no free cores to handle these P threads. I really wanted to maximize the impact of the polling. Swept the polling frequency from less than 1 hertz up to 5 kilohertz. And the two rows at bottom are the total runtime and the linear solve compared to the baseline application run 5 times each for averaging, but to look at what the overhead really of these parasitic P threads are. I thought the linear solves probably would be more stressing. I'm surprised that wasn't the case actually. The linear solve is really where MPI is most active, and I expected that to have the most impact due to any kind of thread overhead breaking the synchronicity in there. But regardless, what you can see is that the overhead is less than 5% of runtime up to 500 hertz polling. So trying to maintain the lightweight design goals, and it seems to be the case so far anyway. Lastly, one of the features that I found useful anyway is the ability to perform memory actions based on thresholds. So in this case, I've set the GPU memory tripwire to 4 gigabytes. Based on the previous example, I knew we were going to exceed that. And in this case, what happens is when the thread detects that the GPU memory has exceeded that amount, we call one of several actions. In this case, we simply print a stack trace and abort. So again, similar to peak mem usage, wanted to maintain the MPI functionality. In this case, there's a couple ways to run under MPI. The first is still using LD preload to get this into your application binary. I will say a little bit frustrating that while there is a standard for how MPI exec should work, there's no standard in how MPI exec passes environment variables to applications. So this syntax is OpenMPI specific. I think you need something a little bit different for MPT and something different for MPitch. So, 25 years on, here we are. But it works. Perhaps more easier, I'd say, from the MPI application is if you link directly with the library, then you don't have to worry about LD preload or any of that nonsense. Results are still the same. Everything's the same under the hood. But that does present some additional options. One of the things that the tool does provide, in addition to that's enabled by direct linking, then is a very minimal API. So if you install a tool, there's a header file that comes along with it. It allows for a number of things. It'll give you, you can call in and get the current memory usage that it's aware of. It'll report that directly to you through its API. But maybe more useful for a developer is to annotate the log file as well. So if you simply making calls into the API to annotate the log file, you get whatever string you stuck in there, so you can really see what parts of your code are driving which aspects of the result. Same tool here, in this case, run on my laptop with no GPUs, so we'll only get the 2 columns of output. So that was all fun. In my mind, there's still a lot to do, and there's a fair bit of that's underway, and some of it's a little bit more formulative. So I want to talk about that and then get just general feedback and feature request type stuff. So the biggest limitation probably is that the tripwire functionality is reactive. You're polling on a P thread, even at 500 Hertz. Detecting you've exceeded a limit is not quite as helpful as stopping short of exceeding that limit in the first place. To do that more robustly, you really need to interface directly with malloc and free to catch the offending memory request before you go over the threshold. That opens a whole lot of complications, but it's pretty well supported at present with an optional configure argument. If you go down that path, there's 2 different approaches I'm pursuing in this regard. 2 additional shared libraries will result. One is a malloc override, and this is still suitable for the LD preload approach. It has versions of malloc and free, which then use LD sim and to call the operating system provided ones with some tracking functions up front. So it works pretty well. I would say it gets a little bit more complicated with the depth of the software stack. The second approach requires direct linking, but it's more robust. There's a fun feature I found in the Linux linker through all of this, wrap symbol. The Linux linker allows you to wrap any function that you want simply by specifying it at link time. What that does is it takes all defined references to that symbol and replaces them with real symbol. It takes all undefined symbols to that, references to that symbol, and replaces them with wrap symbol. So then you just simply write, in this case, wrap malloc or wrap free, and that's what's going to get called for every piece of your software that calls malloc free, calloc, realloc array, etc. And so that works pretty well, but again, you have to directly link rather than resort to this LD preload trick. What that looks like is something more like the following. Not terribly surprising. A number of tools do this sort of thing, but what's different is the ability to take application action based on a specific memory event that may occur. So in this case, we're wrapping malloc, calloc, realloc, and realloc array, all of the C-based memory functions that are available on the operating system. These also get invoked by Fortran and C++ in almost all cases I've encountered, or in every case I've encountered. So this is a pretty robust way to actually catch the memory request before the exceedance occurs. Finally, the last direction is additional MPI functionality. Currently, the library does not require MPI to compile, and that's pretty nice, but it does limit useful application termination in several ways. So at the moment, if you were to use this tripwire functionality, that just causes a process to abort. It doesn't call MPI abort because, again, we're not using MPI. Depending upon your MPI implementation, that might be fine, or it might just cause everything else to just hang until runtime exceeds, which isn't great, but that's the state. 2 obvious solutions: we can call MPI abort from inside the library, not a problem. We just need the MPI API, and we need the user to call this, so it really eliminates the ability to do the LD preload path, which would be unfortunate. The other option, and I guess these aren't really mutually exclusive, is that in an abort situation, rather than trigger it from inside the library, just call user code a user function pointer. So the last bit is a little bit more complicated, but I do think important. And task-based, for highly dynamic MPI applications, you could argue that the individual MPI rank memory usage is probably not the limiting factor, but rather that of a node. And so you may want to be able to monitor an entire node's memory footprint from your application. to do that robustly is a lot more complicated, but totally doable. I think what's required there is the user would need to pass in an MPI communicator, that the library splits the communicator and then performs node local collectives to keep track of what's happening on the node. And in order to keep it from tanking performance, we want to do that with asynchronous collectives or non-blocking collectives and rigorous support for MPI thread multiple. So the biggest issue I have there is that it imposes a lot on the host application and might limit uptake. So, but that's the direction I see it going. So with that, I thank you for your attention. I realize I'm the last thing between you and a beautiful Colorado spring afternoon. And so happy to hear any thoughts, feedback, or other future ideas.
I have a thought. Sorry, I wasn't here for the whole talk. I've always been interested in trying to memory profile my applications, but we found memory pool libraries to be pretty beneficial for performance.
For like allocators?
Yeah, just like Umpire and things that do, allocate 75% of the memory, and then you don't call malloc or calloc directly. And I'm not super familiar with them enough to know if there's like an interface for those to be able to read this type of information, since they've already allocated the memory. And then using a tool like this, you're probably just going to see a flat line unless you go over it, right?
Yeah, I think you're probably right. So I've became aware of the gperf tools through some of the development here, and it has a number of memory allocators as well. Yeah, I think your mileage may vary on how you're like if you have a very dynamic AMR object-oriented code, you can see substantial benefits from pool type allocators. And I've not used this in concert with a pre-allocated buffer size, but that'd be a good use case.
Thanks for the presentation. It's really a great tool. I was wondering, like, if Valgrind or VTune, do they have the same functionality for CPUs? I'm not aware of GPUs, but at least CPUs.
So Valgrind has a really great tool called Massif, which will give you, it'll periodically sample, and then it keeps track of the high watermark and gives you a function by function histogram, even by data structure. And it's great for really, trying to minimize your memory footprint or selecting data structures to give you smaller memory footprints. For production runs at large scale, it's just so slow and cost prohibitive and introduces a lot of overhead itself.
Are the same kind of issues with VTune. Like if you run VTune, even for a couple of seconds, they will generate several gigabytes of information, which is sometimes difficult to pass out.
Yes.
And second issue, which I feel like this tool is good when your program doesn't segfault, but what if it segfault because of the memory issues? And can you predict like where exactly it was segfaulting or which malloc call was doing things?
If it segfaults because you had a malloc that didn't return because you requested too much. So it would rely on the secondary capability I implemented, where basically it would take an iterative approach, right? First, you need to know what's happening. Then you want to set a threshold below the amount of where you ran out of memory and catch. And here's where it gets a little bit complicated, right? You don't want to catch the thing that requests 10 bytes. You want to catch the next thing that requests a gigabyte. And it could be MPI. It could be your IO subroutine. It could be your own application. And that's where the synchronicity gets really hard to predict as well. So you need to really catch everything in the application stack that's using malloc.
Are you running just one thread for each MPI process, or like you're running each MPI process is having one corresponding thread, which is finding out how much memory is consumed by that process?
Every rank spends a P thread. And I was obviously very concerned originally that would cause a lot of contention, right? The good news is these threads are not doing flops. They almost have no memory requirement themselves. They just periodically make operating system calls. So apparently NanoSleep does a great job of scheduling them to run later. And, unless you just get really absurd and all you're doing is, 5 kilohertz calls down to operating system and parsing files out of proc, it doesn't seem to have a notable benefit.
does nano sleep works? Like I tried one time nano sleep or micro sleep, but it has a lot of like, even if you say, well, I want to sleep for 1 nanosecond or 10 nanoseconds, it sleeps milliseconds, not for the
Right, right. Yeah. So nanosleep's a POSIX function that guarantees you'll sleep at least X, right? And it makes no guarantees on how long you might sleep. So under heavy load, you can sleep longer than what you request. And I do see that, if I say, hey, I want to sleep for a second, I might get woken up after, 1.1 seconds, 1.3 seconds. And so that's where the reactive approach is a little bit limiting. And if you really want to catch the memory exceedance the second it happens, you need to get down in the malloc layer. Thank you.
One question I have, might be trivial, but just curious. Typically, I mean, in our system, we run an NPMD application, so you'll have multiple executables. How's the functionality of this tool with an NPMD application? Is it just kind of the same out of the box, or is there any extra complications you have to think about?
So if you want to do it, depends on the LD preload option, you would need to either propagate to each binary.
Okay.
And I can only imagine what the MPI exec looks like, and it's
it's going to get massive.
Alternatively, if you're willing to link to it or relink to it, then you can selectively choose which binaries that you want. Either approach will let you.
Okay, so you could granular, you could do granular, just focus on one application within it. Okay, and then also, I'm not. It looked to me like the examples were either OpenMP or MPI. Does this work with a hybrid application?
Yeah.
Okay.
Sure.
Great.
It does. Yeah, and I mean the one of the things I didn't really harp on though is like the log file name. It depends MPI rank, and it by default it's memory usage.log, right? So at scale, it's going to dump 50,000 output files into your current directory, which is probably not what you want, But you can redefine it to a node local temp and then aggregate after the fact and that sort of thing.
And with that, let's thank all of our speakers from today one more time. And thank you to you all for joining us today, and we hope you join us again tomorrow.